Yeah, good afternoon, Dr. Prawn.
Good afternoon. Let me just sort my slides out. How is everything going so far?
Yeah,
Things were great.
Good.
We had around 70 participants in the morning.
Okay.
And now they're going to join again. There was a break. There was a lunch break now. So people are joining.
So may I share my screen now and set this up? Is that appropriate?
Yeah, we can just have a test of it. People will be joining by 2 o'clock. We'll start sharp at 2.
Okay. Can't even see any of that. Got it.
yeah, it's visible, sir.
Yes, sir, it is visible.
Okay. And we've definitely got it on full screen. Be reassuring if you could see it yourself.
Yes, yes. It's
Yep.
clearly visible. Full
I
screen.
think we can keep it as it is, no? Let it be.
Yeah. We can keep it on.
Better. Yeah. Reena madam, we'll keep it as it is, okay?
Yes, sir. We'll keep
Yeah,
it.
we'll only. So,
So how are things, sir, back in UK?
Oh, things are okay. It's lots of people have had various COVID jabs by this point in time.
Oh.
But the situation here is still nowhere near normal.
Yeah.
But I think you face some greater challenges than we do at present.
Yeah, we are way below normal. We are way below normal. I don't know when it's really going to come up. I mean, we would be in the normal mode. Otherwise, this would have been a physical event altogether.
Yes. Well, it would have been nice to travel to India again. It's a little while since I've done that.
In fact, I'm waiting for your arrival in India.
Yeah.
But now things, I really don't know when we are going to get back to normal. Really.
Yeah. There probably will be some version of normality before very long.
Right.
and sir, whenever you come to India, give us a chance to host you.
Thank you.
Yeah. And Mumbai is in international airport, so no problem. You have to come
Yes.
to Mumbai only. And
Yep.
international airport is hardly 4-5 kilometers from.
Actually, the planes
our institute.
land. Actually, when the planes are landing, they fly over SPIT.
Yeah.
Yeah.
I think Dr. Rao is there. Yeah. Rao sir, we have the general chair, our Dr. Y.S. Rao, who joined this piece as well.
Yeah, good afternoon, Michelle.
Yeah, I want you to introduce that. So we have our general chair of the conference, Dr. Y.S. Rao. And
Oh,
yeah,
a great
sir,
pleasure to meet you, sir.
Yeah, good afternoon, sir.
So I hope your conference is going well, Dr. Rao.
Yeah, it's the first day.
Yes.
Yeah, first day skill development, then contributions.
Yes. Good. it's a challenging time to be holding such a conference.
True.
Yeah.
A different conference first time, and hopefully this kind of conference should be last conference. We want to have physical conference.
It's very difficult to know, but it may be that sometimes these online events open up new opportunities in some different ways. So
Yeah,
I think that's the only way we can view these things.
yeah, a lot of time saving,
Yeah.
money saving, traveling.
Yes. Better for the environment. Yep.
So shall we start? I think we should
Yes.
go ahead.
Yes, yes, sir.
Yeah. Reena ma'am, you can.
Okay. Okay. Good afternoon to one and all. First of all, let me assure you that this afternoon would be remembered in the history of SPIT for the long time, as I feel very proud and honored to introduce our next distinguished speaker. But before that, let me take a moment to talk about his contribution in the field of embedded systems. He was awarded a BSc Electronics and Electrical Engineering by the University of Southampton, UK. He is a founder and CEO of UK-based Safety Systems Limited, a company which provides supports for organizations that need to create real-time embedded systems. Over the past 2 decades, he has been working in the field of time-triggered embedded systems and helped numerous companies to create successful TT designs. Many of these designs have been produced in compliance with international safety standards and guidelines, including IEC 61508, ISO 26262, and DO 178. Previously, he was a professor of embedded system engineering at the University of Lancaster, UK, where he established the Embedded Systems Laboratory, invented the PTTES pattern language, and led teams that developed the NISA safety agent and the first single and multi-core processors that were designed specifically to run TT software. During this time, with the University of Lancaster, he supervised more than 20 successful PhD projects. He is also an author of several successful books and more than 100 technical papers. He is named inventor, co-inventor on a number of patents and patent applications. Some of his popular books are the Engineering of Reliable Embedded System and Patents for Time-Triggered Embedded System. It is my privilege to welcome an author, an entrepreneur, and a great leader, Dr. Michael J. Pont. I request, sir, to please share some words of wisdom and enlighten all of us with his wealth of experience and knowledge. Over to you, sir.
Well, thank you very much. I hope everybody can hear me. That was a very kind introduction, thank you. And I'd like to also thank the conference organizers for giving me an opportunity to present today. So this is the topic of my talk. I'm going to talk about the foundations of safety-related and safety-critical embedded systems. And I'll talk about what I see as a gap between prototypes and compliant systems and how that gap can be bridged, in my view, using time-triggered software architectures. I'll explain what a number of these terms mean over the course of the introductory slides here. So I'll explain what I mean by a safety-related and a safety-critical system, and I'll outline what I mean by a TT software architecture. So I've been developing time-triggered software systems for more than 30 years now. I began my work on my first commercial embedded system in 1986, and I've since worked extensively on various TT systems, first in the university sector and then in industry. I didn't invent TT systems, those existed before I began work in this field, but I think it's fair to say that I helped to popularize this approach, starting with the book Patterns for Time-Triggered Embedded Systems that was published nearly 2 decades ago. I founded my present company, Safety Systems, in late 2013. I worked on various successful TT projects, from space-based systems through to simple household goods and sports equipment. I've worked on a number of different projects. Most of these projects are under the terms of non-disclosure agreements, but you can find information about 3 recent projects that Safety Systems has conducted in the automotive, industrial control, and medical space on the company website. And I will say a little bit more about these recent projects towards the end of this talk. In this talk, I'm going to assume that most people joining the talk are attending the Microdevice TT training day that's running at this conference, and that they will know a little bit about TT systems. But I'll say a few words about what a TT system is in the course of the next few slides. So this is what I'm going to try and do during the course of this afternoon. My goal is to explain why TT software architectures provide a suitable foundation for many safety-related and safety-critical embedded systems. I will explain how TT architectures are used in such systems. I'll talk about some of the different characteristics of industrial control systems, automotive systems, and medical systems as I see them. And I'll provide my perspective on the differences between the use of a TT software architecture and a conventional real-time operating system, or RTOS, in safety-related and safety-critical embedded systems. There will be a Q&A session at the end of this talk, and if you have questions, I'll be happy to try and do my best to answer them at that point. So these are some of the definitions of the terms that I'm going to use in this talk. If a safety-related system fails to operate in accordance with its specification, people using the system or those in the vicinity of the system may be injured. If a safety-critical system fails to operate in accordance with its specification, people using the system or those in the vicinity of the system may be killed. A prototype of one of the above systems is sometimes based on a traditional RTOS. This is because, in my experience, this is the approach that's taught in many universities and colleges and is supported by many websites. So some people think that this is generally the only way to build a system. For example, a prototype of a control system may be based on an RTOS and may allow a vehicle to move around a test track. Unlike a prototype, the type of system that I'm concerned with in this presentation needs to be compliant with one or more international safety standards, such as IEC 61508, which has a focus on industrial control systems, but is the foundation for many other standards. If you want to investigate only one international safety standard and you have no previous experience in this area, I would suggest you try and learn a little about IEC 61508. The safety standard that's most commonly associated with automotive systems is ISO 26262, which was adapted originally from IEC 61508 to meet the particular needs of automotive systems. Another related standard that's also linked to IEC 61508 is IEC 62304, which has a particular focus on medical systems. The key difference between the prototype design in the line above and the compliant system is that by the time we get to a compliant system, we have to be confident that the system will operate safely. And one of the differences that is sometimes seen, for example, is that in an automotive system, for example, in the prototype, there will be what's almost universally known as a big red button on the dashboard during the prototyping of the system. So if you're running around a test track and somebody sitting in the vehicle hits that big red button, the vehicle will come to a halt. And that gives you reassurance during the prototyping phases that if anything really strange or unexpected happens with the control system that you've developed in the vehicle, you've got a means of shutting it down. The key distinction is by the time you get to the compliant system that's ready to release to customers, there is no big red button. So by that point, your system has to be capable of determining for itself, in many cases, whether it is operating correctly. And it has to have the ability to bring the system into a safe state in the event that problems are detected. So the world looks something like this, in my view. People build a prototype, typically based on a conventional real-time operating system. And they need a system, ultimately, that's compliant with one of the international safety standards. A common misconception that I encounter many times a year is a view, now we have a prototype, we'll be ready to start production in 2 to 4 months. In practice, it can take 18 to 36 months, or often much longer, to convert a prototype into a fully compliant system in which we can be confident about the system safety. And in this presentation, I will argue that the use of TT software architectures can help to reduce this gap between prototype and compliant systems by a factor of something to something in the region of 6 months. Sometimes a little shorter than that, sometimes a little longer than that, but generally it's difficult to be confident that you can meet these requirements in something less than that period. Generally, in my view, people grossly underestimate the work required to demonstrate that their system is compliant with one or more international safety standards. And my goal in this talk is to explain why that is, and to explain why, in my view, TT software architectures are a good way of bridging that gap. So very briefly, I'm going to try and explain what a TT software architecture means. So what we have in a TT design is we start with a very simple software framework. I'll give you a couple of examples of that in a moment. The system is so simple that we're able to model the behavior very precisely using what are known as tick lists. And again, I'll give you some examples of what that means in a few minutes. So we then build our system based on the above model. And we then incorporate a different representation of this model in the final system and use this to confirm at runtime that we're obtaining the required behavior. So essentially, we are building our system in such a way that the architecture is so simple that we can model the system behavior very precisely. We model that behavior at design time. We then take that model and we incorporate a representation of that model into the system, and we continuously check against that model at runtime to make sure the system is operating correctly. It's extremely powerful. And these steps allow us to provide very clear evidence that we've met the system safety requirements and the related requirements of international safety standards. And again, I'll try and say a little bit more about each of these stages as we go through this talk. One other thing I should have said at the beginning, I believe people who are attending the conference will already have received or will receive a copy of the presentation slides that I'm using here to refer back to after the presentation. So if we talk about time-triggered systems, when we say that an embedded system has a time-triggered architecture, we mean that it executes at least one set of tasks according to a predetermined schedule. The schedule determines the order of the task releases, the time at which each task is released, and whether one task can interrupt or preempt another task. Here's a very early example of a TT system. I took this photograph in Belgium. It shows the carillon mechanism in the belfry in Ghent in Belgium. So this is essentially a clockwork mechanism. So that large brass drum rotates, and if you can see my mouse on the screen, you insert prongs into the drum. And when these prongs pass the top of the drum, they cause a bell to ring. So what happens is every 15 minutes or so in this design, a tune is played by the bell tower. And the tune is the same every time the tune is played because of the positioning of these spurs. So this is basically executing a predetermined sequence of musical notes, and the same predetermined sequence is executed every time. And if you ask the people in Ghent whether the clock was functioning correctly, after living in the town for a couple of years, they'd probably be able to tell you whether the mechanism was running quickly or slowly, and they'd certainly be able to tell you whether one of these prongs had become missing for the drum because they'd noticed the difference. And that, in essence, is what we're trying to do with a TT software design. We're trying to produce the system in such a way that the behavior is completely deterministic, and we can easily determine whether something has gone wrong. So in practice, the usual starting point for such a design is a bare metal software platform. By that I mean there's no RTOS, there's no Linux, there's no Windows, or whatever you might have expected normally to include on this system. Some people assume because a laptop computer is running Windows or similar, and their mobile phone is running Android or similar, that a computer needs some kind of operating system. That's not the case for the kind of systems that we're concerned with in this talk.
Yeah.
So we have a bare metal software platform with no RTOS, no Linux, no Windows. We've got one active interrupt per CPU linked to a periodic timer tick. And we're going to poll the peripherals. Let's take a simple example of what that looks like in code. I'm only going to give you 2 outline code examples in the course of this talk. I'm going to be dealing with the concepts, not low-level coding examples. So please don't be concerned if this is not something you're familiar with or you don't even have a software background. So I'm assuming here that we have a system where a timer is generating an interrupt, in this case, every 1 millisecond. The generation of that interrupt triggers what's known as an interrupt service routine that's called update in this example. And every millisecond here, the tick is generated. We have a single function called update called. Between the execution of update and the next tick, the system is put into a sleep mode. We would potentially call various tasks or functions from here, perhaps in a long switch statement. And the end result would be we have a very simple time-triggered system with cooperative tasks. So the tasks are cooperative because they run to completion, and we don't have a situation in this design where one task can interrupt another task. We don't support task preemption in this design. In practice, we're going to turn this into something that is easier to use. So it would be very unlikely that my organization would not attempt to build a TT design for a practical system on a framework that was this simple. Instead, we'd use something that looked a bit more like this. The concept is the same, but we're turning it into a software architecture that makes it easier for us to add tasks to the schedule with particular characteristics, etc. But the general concept is the same. The system runs, it releases tasks on a periodic basis, and it goes to sleep between the task releases. You'll learn more about these kinds of designs during the tutorial session that's running during the course of today. So sometimes people look at these kinds of designs and they say, okay, that's just not flexible enough for me to be able to build a system. What you're saying is, like that belfry design, your system only plays one tune. It only runs one set of tasks. How can I possibly build a system that is that simple? So the reality does become a little more complicated. So suppose this is the set of tasks that we're running in our system while our aircraft is beginning to rise up to cruising height. When we get to cruising height, the system may run this different set of tasks. And when the system comes into land, we run a different set of tasks again. So in a TT design, this set of tasks, this set of tasks, and this set of tasks have all been considered and analyzed in detail at runtime. And there might be 20 or 30 different system modes used in which the system runs a different set of tasks, but the case will always be the same. Frankly, it's quite tedious at design time, but there are significant benefits to it. We can analyze this in detail because we know that while the system is in this mode, this is all it will do. We assume it will run task A, then task B, then task C, then task D, then task E, and then it will go back and start again, and it will do that, we assume. Similar things happen in these other modes, but we can analyze this behavior in detail at design time. TT designs don't just support cooperative tasks, they also support task preemption where this is required. And these designs can be rendered immune to what's known as priority inversion, unlike designs based on a traditional RTOS. I'm not going to say anything more about that here. I'm happy to say more about that in the Q&A session if people have any interest in that. In many cases, designs involve more than one processor, and a TT architecture extends naturally to such multi-processor designs. So we have, in this case, what's known as a master node, which has periodic timer ticks running on it. And we have, I'm assuming, multiple different processors in our network. Each of these has a microcontroller in it. Each of these is running a simple TT software architecture. The TT software architecture in this node is driven by periodic timer ticks. Every time there's a tick, this node sends a tick message to these other nodes on the network. The arrival of these messages on the other nodes drives a scheduler in these nodes. So in this process, we can synchronize the activity across multiple microcontrollers. So everything's running time triggered and everything is synchronized. So these different microcontrollers may be at opposite ends of a factory. And these microcontrollers may be on the same PCB. And I'll give you some examples of designs based on a single PCB shortly. So the point of all of this, of building our designs in this way, is fundamentally so that we can model them. So if we take a step back from this again, this is an example of a simple design in which the task sequence that's triggered is A, C, B, D, and then A, C, B, D, and we assume it keeps running these same sets of tasks forever. Unless the power is removed or we change into a different mode where we're going to run a different task set. So this is known as the tick list that represents that system. So in tick 0, we run task A, task C. In tick 1, we run task B, task D. The point to emphasize here is this is always what happens when the system is running normally in this mode. There is no variation to this when the system is running normally and in this mode. Because of this, we can make a number of calculations and assessments based on our tick list design. We can determine the system response times. For example, we can work out precisely how long it will take the system to respond to me pressing an emergency stop button. Exactly how long is it in milliseconds or sometimes in microseconds before that system begins to shut down? We can work out the task jitter levels. That's the variation in the release time of the task. So for example, is how much variation is there between the start time of task C here and the start time of task C here? If the jitter is 0, there'll be no variation. They will always run exactly, for example, 20 milliseconds apart. If there's variation, then sometimes they might run 19 milliseconds apart, sometimes they might run 21 milliseconds apart. That may matter a great deal to you if this task has particular real-time constraints, or if, for example, it's involved in an analog to digital conversion calculation, or reading inputs for your system, or generating outputs from your system. You may need to know. We can determine that from the tick list. Another thing we can determine is the maximum CPU load. I'm just going, because we can do that easily, within a couple of minutes, I'm just going to give you an example of how we can determine the maximum CPU load for this kind of system, as an example of the kind of things we can do with a tick list at design time in a TT system. So typically, there may be requirements from the customer. For example, we might have a requirement that the CPU load must not exceed 50% at any time during normal system operation. I have seen this requirement in several aerospace designs. The typical reason for this is an expectation that at runtime there may be situations in which the CPU load is higher than the designer expects it at design time, and we don't want to try and attempt to run the system at greater than 100% load. To give us some headroom, the designs may have a requirement that the CPU load must not exceed a particular limit. There's another factor here, and another key question that relates to this. Often we need to know whether we can add an additional task to the system without having an impact on the existing task set. This is a frighteningly common requirement. Many designs go through the process where this customer draws up a specification. We agree the specification with the customer. We then take the design to the customer, and the customer says, that's great, but really what we meant was this. We didn't realize that was exactly what it was going to do. And really what we meant was this, or this would be even better if it could also do this. Changes late in the design process are a fact of life. And we have to produce our systems in such a way that we can make changes without having to repeat what may be a very long and complex test process to confirm that everything is operating correctly. So we have two key challenges that we're trying to work with here. We need to make sure that there's no risk that the system will exceed its expected CPU load, and we need to be able to add additional tasks to the system without having an impact on the existing task set. So this is how we do this in a TT design. Let's assume this is the complete hyperperiod, by which I mean simply that this is the task sequence we have. It runs the task sequence A, B, C, D, E, F, G, H, and then it goes back around to the beginning and it runs A, B, C, D, E, F, G, H again. So that is our complete representation of our task sequence. For each tick, the interval between these timer interrupts, we look at the tick interval and we sum up the maximum execution time of the tasks in the tick, and we look for the tick where the task worst case execution times are highest, and we treat that as our maximum CPU load. So for example, if the tick interval here was 10 milliseconds, and the sum of the execution time of task E, of the worst case execution time of task E and task F was 9 milliseconds, then we'd have a 90% CPU load. In a TT design, we may be able to justify that because we know at design time that the load is not going to exceed 90%. And at runtime, we're going to monitor that load precisely, and we're going to confirm that nothing has happened to the worst case execution time of this task or this task that would undermine our assumptions. And we can therefore check exactly that we're going to achieve this result. To meet our second goal of being able to add tasks to the schedule, we can also do that. So we could, for example, add a task X to this schedule in at this point here, provided that this task did not exceed, did not mean that there would still be a task running when task C was due to be released. So provided we can meet that goal, we can add a task X to the schedule here, and we can do that very late in the day during the product development, because provided we monitor the execution time of the additional task and make sure that it cannot exceed the limit here, we can be sure that this will not interfere with the other behavior that we've seen in the system. This is extremely powerful. The alternative in a traditional RTOS-based design is any changes, even a tiny change, can have a ripple effect that mean absolutely everything has to be tested again. And that can be an enormous task. We could just end up in a continual cycle of fix, test, fix, test, fix, test for a very long time. So let's say we've built our system, we've modeled it like this. Now we're going to monitor it at runtime. So I've argued that TT designs are easy to model. We can determine the max CPU load, we can determine response times, we can determine the jitter, for example. But these models, if you think about it, are all based on various assumptions. We're assuming that the central processor unit in each microcontroller, MCU is microcontroller in my world, in each microcontroller or processor in the system, we're assuming that the microcontroller or processor is operating correctly. We're assuming that we're running the correct program on each microcontroller. We're assuming that we have an operational scheduler on each microcontroller. We're assuming that we can transfer data between tasks on the same microcontroller without corruption. We're assuming we can transfer data between microcontrollers without corruption. We're assuming that we have operational peripherals on each microcontroller. We're assuming that we know the worst case execution time and possibly the best case execution time of all tasks on each microcontroller. We're assuming that we know the execution sequence of the tasks in each operating mode on each microcontroller. There are lots of assumptions. We're assuming, making assumptions about temperature and other things as well that I've not included in this list, but essentially there are a lot of assumptions. So what we need to do is we need to incorporate mechanisms that will allow us to test these assumptions at runtime. And we need to consider during the development process what we're going to do if these assumptions are not met. And if we do this, and this can be a large part of the design effort, if we do this, then we can have a very high level of confidence that the models we created at design time will be valid in the field. And one thing that's not always appreciated is many of the designs that we create are switched on day one. And 10 years later, without any testing by anybody in that interval, the system is still expected and required to operate in accordance with its specification in a factory or a similar domain. There's no testing, etc. required in there. All of the testing that's required to ensure that this system can continue to meet its specification 10 years, sometimes 20 years after it was produced, must be carried out in the system itself. And you don't get that by magic. You have to design in such capabilities from the start when you're producing your system. So just one example of the way that this kind of thing works for a TT design. We have a scheduler in the system that's working out which task to release. And we have a second representation, basically a list of task releases stored in flash memory that we refer to at when the system is running. So in this design, before we release task B here, So the scheduler decides that task B is due to be released. Before we release task B, we check with a mechanism that we call a predictor whether task B is the next task listed in the schedule. Because that is known in advance, and this is effectively determining the task releases at runtime. So we do a double check using two different mechanisms to make sure that the task release is correct. And again, if that fails, typically we shut the system down. If that's correct, the system carries on. And this gives us an enormous level of confidence that the system is operating correctly. And the absolutely key thing to note about this is we are checking whether we should be releasing task B before we release task B. That's absolutely critical here. So you don't release the airbag in the vehicle and then think, oh dear, I shouldn't have released the airbag. What can I do about it? Instead, you work out beforehand whether that event should be taking place. And that's a fundamental feature of TT designs, and you cannot do that with other designs that are not TT. That's a fundamental and core advantage. There's no magic to that. It's simply because the designs are running in a highly deterministic way, so we can check in advance that we're about to do the right thing. So let's just pull this together and begin to talk about how we turn this into some real designs. So I'll look quickly first at some industrial and automotive designs. So typically these are assembled by having a processor unit, some mechanisms for checking the task sequence, a standard watchdog timer, a mechanism for checking the task execution times. I'm not going to attempt to run through all of these features in any level of detail at all. But we have this core platform that's running a TT system on a single processor. And then we have an external device, and that external device is a formal watchdog. But unlike most watchdogs that some people watching may be familiar with, this doesn't reset the processor. This has the capability of disabling the system that is under control by our design. So our system runs a TT scheduler on the processor and has an additional external component that's also able to disable power, in this case for our electric vehicle. And the reason this architecture is used is we only feed this watchdog if the scheduler is running correctly. So if something has gone wrong and we can't run the scheduler, for example, this processor has failed power on self tests or failed another test during its operation, or has simply gone haywire and isn't operating as we expect, the scheduler won't be running correctly, we won't feed this, and we will disable power to the external source. Another simple example, typically I can destroy this processor by applying 10 volts to it, for example. I would typically have my external watchdog device capable of withstanding a much higher voltage. So in the situations where this was disabled and possibly left in a dangerous state, this would still be able to pull me into a fail-safe state. That's one potential design. Another popular design, particularly in industrial control systems, has two microcontrollers running. And they continually run and they continually perform cross-checks between them. And that's a very powerful architecture, widely used in many industrial control systems, typically based on small microcontrollers that are each individually costing no more than a few dollars a piece. But they're doing cross-checks between them and giving you a very high level of confidence that this system will operate correctly. And in this kind of design, it's fail-safe, which means that if either of these processors detects a problem, it will pull the system into a safe state. Essentially, it will shut the system down. And the way that that typically works here, for example, some of the monitoring on here, the task sequence for this microcontroller will be checked by this microcontroller and vice versa. That's some of the cross-monitoring that we can perform in these circumstances. So we have a system set up here, a typical example for industrial control systems based on two small microcontrollers with cross-checks between them. Many designs, typically automotive designs, require fail operational behavior. So if we consider what fail-safe behavior means, if we consider these industrial robots, if a problem is detected in the control system of these industrial robots, we can safely shut the system down. So we can safely just stop the robots in most circumstances. In this situation with an automotive design, in this case on a level crossing, where there might be a train coming, or any point at which the vehicle is traveling at speed, perhaps on a motorway with other vehicles around it, we simply cannot shut the control system down. We need some kind of fail operational behavior to ensure that this system will continue to operate, at least in a limited form, in the presence of faults. And a typical architecture for that in a TT design would involve two processors with cross-checks, as we've just outlined. But in this situation, if we lose one of the processors, if one of the processors fails, we assume that we're still able to continue to operate the system, possibly with reduced performance or some level of restricted functionality. For example, in a vehicle, we might have reduced maximum speed, but we'd still be able to run the system on a single microcontroller to at least get this vehicle safely to the side of the road, or move it off a roundabout, or move it off a level crossing. So in many cases, we have to provide this fail operational behavior. In general, if a customer comes to us and says they require a design that's fail safe, that's good, because life is much easier. Obtaining fail operational behavior is generally much more challenging in a design. There's another class of systems that I also want to just briefly touch on here. And this is called what we call a TT wrapper. So sometimes it's possible to build a complete TT system. In other sense, we can only build a TT wrapper around an existing system. So what a TT wrapper is, it's a monitoring unit that's used to improve confidence in the safe operation of a pre-existing complex component or system. So the system being wrapped is not usually TT, and the system being wrapped may contain unqualified software or hardware components. By unqualified, I mean these are components that weren't designed originally for use in safety-related systems. So for example, it might be hardware that was originally designed for use in a mobile phone or a laptop computer, rather than being intended for use in a safety-related design. In terms of software components, it might be Linux. And this is a common requirement. Many systems, particularly in the medical domain, have large elements of software incorporated in them, typically involved in things like the user interface and sometimes in communications processing, that weren't originally designed for use in safety-related systems. So ideally, we would rework the entire system in an appropriate manner. And in my case, I'd want to recommend the system was completely rebuilt using TT software. But in reality, that's often simply not practical. So we have to deal with the fact that we may have systems which contain large numbers of components that were not originally designed for use in a safety-related system, and we need to now try and make the system safe. So this is a common term that's used in the medical domain from IEC 62304. It's SOUP. And what that stands for in this context is software of unknown provenance. And in the context of IEC 62304, this means software that wasn't developed for use in medical devices. So we may have a system that's running software of unknown provenance, And it may be running on a platform that may include hardware of unknown provenance, which again is standard off-the-shelf hardware that wasn't originally designed for use in a safety-related system. So in that situation, we may introduce a TT wrapper into the design. So what this does typically is it performs continual tests at runtime while the system is operating to provide confidence that this often much larger and quite complicated system is operating safely. And if the wrapper is unhappy, then the wrapper will usually have the options of either resetting the original processor and seeing whether that helps, or simply shutting down the medical device of whatever it is that's under the control of this and then monitored by this. Over recent years, a particular area that we've been asked to look at several times is existing designs based on Linux or similar platforms. These are very popular. Lots of people do prototyping on this, and then they need to take this system and turn it into a working product. That can present significant challenges. It's often not practical to rework all of this. There's something like 20 million lines in Linux code, 20 million lines of Linux code here, plus the application code. So sometimes the only practical option is to add a wrapper like this. One constraint on these kind of designs is, two constraints. First of all, it's not always possible to identify a means of implementing a TT wrapper. Just because you've got a Linux-based design doesn't mean that we would be able to help you turn that into a safety-related system. It may simply not be possible to identify a set of tests that would give us sufficient confidence to say that this system was operating correctly. So it may not be possible. Where it is possible to do this, this is almost always going to be a fail-safe design. Because we usually know if this goes wrong, we can't usually determine what has gone wrong. There's not usually very much we can do to recover that. So all we can usually do with this is check that this is operating correctly. And if it's not, try and move the world into a safe state. So we can't usually make a fail operational design based on this platform. We can only make a fail safe type design. So let me then just take a step back here and say, if you were designing your system, what are the reasons that you might wish to avoid use of a conventional RTOS and consider a TT approach? I'm going to run through some of these things from a slightly different perspective. So from the perspective of many people, what I propose at the start of many projects looks to the development team to be almost total madness. Many developers have been brought up to use an RTOS or to use Linux, and many developers are used to using large numbers of interrupts. And the general reaction sometimes from teams, if we begin a conversation, is Pont is mad. And this just doesn't make any sense at all. Why would we want to do any of this? So let me try and give you a couple of simple starter examples for that. Suppose there are two planes on the runway. Mumbai International Airport, let's say. And we have two planes on the runway. Both have passed all of the necessary pre-flight tests. One of them contains 10 million lines of code, and one of them contains 20,000 lines of code. Both have passed all of the tests. If you ask most software developers which plane they'd rather fly, they will almost universally want to fly on the one on the right. They want to fly the plane that's got based on the smaller code base, because we all know that it doesn't matter how good your software development team is, there are bugs. And the more code there is, the more likely there is to be bugs. So the starting point advantage from a TT design perspective is the software is extremely simple. And when the code is very simple, it's more difficult, it's less likely, we can have a higher level of confidence that there won't be as many bugs. I'm not saying there won't be any bugs, but the chances are reduced that there will be bugs. Another perspective on this. Many people are familiar with the C programming language. The MISRA C language is generally considered to be a safer subset. So MISRA C basically defines ways in which you can view MISRA C as a set of rules for describing how you should use the C programming language in safety-related systems. And effectively, it can also be viewed as a safer subset of the C programming language. So at the simplest level, MISRA C says don't use the goto statement in your C programs. There are lots and lots of other rules and guidelines built into it, but essentially what it's saying is use this subset. You can do lots of things with the C programming language. If you're building a safety-related system, don't use all of those features. Use this reduced set of features. And if you simplify the language in this way, it's more likely that your systems will operate safely and reliably. My argument would be that systems based on a conventional RTOS with multiple interrupt sources, the same basic consideration applies. TT systems are not something radically different. Both real-time operating systems and TT systems are based on periodic tasks. It's just that a TT system, a bit like MISRA C, adds some additional constraints. And those additional constraints have a profound impact on how we can, and on a level of confidence in the behavior of the system. It's not just me. The core international safety standard IEC 61508 says that TT architectures are highly recommended for systems with safety and integrity level 2 or above. And safety integrity level 2 is safety related systems. Static synchronization of access to shared resources, which is a key characteristic of all TT designs, is recommended in safety critical designs and highly recommended in the highest level of designs that are supported by IEC 61508. The limited use of interrupts, another defining characteristic of TT designs, is recommended or highly recommended in all IEC 61508 designs. The basic reality is I've taken TT designs for assessment by third-party assessors on many occasions. I've never had a third-party assessor turn around and say anything other than, this is TT. Good. That's going to make life much easier, because that's essentially the situation that we're in. So the key requirement when we're producing safety-related systems, for example, like this washing machine. A washing machine may appear fairly innocuous, but in fact, it presents quite a few safety challenges. And the key challenge is that drum is going to rotate at something like 1,000 RPM and possibly quite a lot faster. You're going to take this device, perhaps, and put it in your kitchen. You're going to have your toddlers wandering around the kitchen. If this device was in a factory, it would probably have a light curtain around it because it's potentially dangerous. In your kitchen, all you have between you and your small child is the door lock on this design. So we need to be confident if we design a control system, even for something apparently as simple as a washing machine, we need to be confident that we can provide the evidence that we've met the safety goals. And providing and documenting this evidence is a key cost factor and a key factor for late delivery of many projects in my experience. And if we get it wrong, we risk releasing products that are unsafe and unreliable. This documenting bit is another key factor. In my experience, most teams hate writing documentation. And anything you can do to make the documentation challenge smaller is a good thing. If the documentation is easier to write, it's much more likely it will be written properly by the development team, in my experience. So, as I outlined much earlier, we've now seen some of these stages here. TT provides a model, build, monitor type methodology. So we're going to use a simple software architecture. We're going to build a model, and we're going to build the system based on the model, and then we're going to monitor the model at runtime. So when compared with projects based on a conventional RTOS, the highly deterministic behavior of TT designs makes it much easier to provide the core evidence that we're trying to find in these situations. My argument would be that this results in reduced development time because we've got the modeling, monitoring, and self-test capability. Unlike an RTOS, we don't have long fixed test cycles, and we can support this process with a comprehensive documentation suite. We saw that you can, with a TT design, work out what the maximum CPU load is by modeling the design. That has another significant implication. Because we can model the processor load precisely at design time, we may be able to use a smaller processor and a cheaper processor because we can be confident, highly confident, that the system will not exceed the predetermined processor load. So rather than having to put a more powerful processor in the system just in case, we can use a cheaper processor that's precisely matched to the needs of the application. We have, in a previous non-safety related project, produced designs that run with a 99% CPU load, because we can do that completely confident that the system will never exceed that limit. That can be very powerful in many situations. For high volume products, being able to use a lower cost microcontroller has very significant business benefits. Overall, I believe that use of TT architectures in an appropriate way means that your projects are more likely to be completed on time, and your organization can be confident that the product will operate safely and reliably. And what that means as a bottom line for organizations is reduced corporate risk. And that's a key factor for many organizations. Let me close the main part of what I want to say here with 3 examples of designs we've worked on recently. So this is an industrial control design example that we've completed recently. In this case, we were developing control systems for balers. So these are used typically to compress cardboard or other things by supermarkets and similar organizations. They receive large amounts of packaging material. They press these into cardboard bales, and then they're taken away for recycling. So this baling operation has some key safety requirements. If the door of the baler is opened and somebody puts their hand in and the baler starts, somebody could be badly injured or potentially killed. So we've designed a control system for this that meets the safety requirements, and it was significantly more cost effective, I believe, than the designs that it replaces. Another example, during the current COVID crisis, we were asked to help on one of the UK's emergency ventilator designs and on a similar design in Australia. We worked on various other medical designs as well. Another design we're working on, this time a UK-based organization that's developing a range of electric trucks, and we've been helping with numerous control systems that are used in those trucks. Further information about all of these projects, a little bit more information is available on our website. One other area that we've been working in is on autonomous vehicles, and we were asked to I was technical author on the UK's first set of guidelines for developing and assessing control systems for autonomous vehicles. That's available if anybody is interested from the BSI website and can be freely downloaded. So it's a short document that provides the UK's guidelines for developing such autonomous vehicles. That's where I'm going to stop. I think I'm just about on time. So I'm just going to summarize what I've tried to say here. There's a gap, in my experience, in many projects between the stage when people have produced a prototype, typically based on a conventional RTOS, and their expectations about how long it will take them to turn that design into a system that's fully compliant with the international safety standards. And it's a common misconception is many teams tell me their heart sinks. They've shown their manager the vehicle moving around the track, for example, and the manager then says, that's great, now we can go to production. The team say, but there's lots more we've got to do to make this safe. But that gap is not always seen by the management team. If we build this with a TT design, it typically takes us about 6 months to convert the TT prototype into a fully compliant system, including generating all of the documentation. The reason for that is the designs are fundamentally based on deterministic behavior and can be modeled using tick lists. There's nothing particularly surprising about this. It's simply a consequence of what a TT design is. So we can do also, in addition to the monitoring, we can do extensive modeling, we can do extensive monitoring at runtime. So this is what I've tried to explain over the course of the last hour. I've tried to explain why TT software architectures provide a suitable foundation for many safety-related systems in which people may be injured, or safety-critical systems in which people may be killed. I've tried to explain how TT architectures are used in such systems, and I've given you some examples of the different characteristics of industrial control systems which tend to be fail-safe, automotive systems which tend to be fail-operational, and medical systems, some of which involve SOUP, software of unknown provenance, or HOOP, hardware of unknown provenance. And I provided my perspective on the difference between use of a TT software architecture and a conventional RTOS in safety-related and safety-critical systems. Thank you very much for taking the time to join this talk.
Thank you, Dr. Michael Pond. Thank you very much. We had a great session. So participants, this is the time for Q&A. Please put your question in the chat box, or you can raise hand and we will unmute you.
It's the time when I work out if everybody's gone to sleep.
Yeah. Sir, I would read question for you, or you can see.
Oh, it's okay. I can see that. Okay, so our starting point typically is around about a microsecond of jitter is acceptable. By the time you get beyond a microsecond, you start to see a degradation in the response times, degradation in the behavior of many systems, but it will vary. It will vary enormously. If your system is only dealing with digital I/O, doesn't have any analog processing, you may be able to sustain significantly higher levels of jitter. But if your system involves, okay, questions coming in now. If your system involves data acquisition, then 1 microsecond would be my starting point. So let me just make sure I'm not missing any here. So priority inversion. So basically priority inversion occurs in a conventional RTOS design when a low priority task, is accessing a shared resource that is also required by a task that is of higher priority. And in a design that's based on an event-triggered architecture, that situation is almost certain to occur. We can't be sure when it will occur, but it's almost certain to occur because we don't know when particular tasks are going to execute. So we can deal with this situation. We can reduce the impact of this, but we cannot cure the problem by doing things like the priority ceiling protocol, which basically means that when a low priority task is accessing the resource, we increase its priority for a little while so that it can finish its activity with that shared resource as quickly as possible. But that process still means that there is some blocking of the higher priority task while the low priority task deals with the resource. If nothing else, that gives you a greater level of jitter, and it's not generally deterministic in terms of the precise timing behavior. In a time-triggered design, if we support task preemption, so most time-triggered designs have no task preemption at all, so the situation doesn't arise. Some time-triggered designs support task preemption. In a time-triggered design, we know when the high priority tasks are going to be released. So a low priority task that wished to access a shared resource, in the simplest design, the low priority task would ask the scheduler before it accessed the resource. And the scheduler would either say, yep, go ahead, access the resource, because the next high priority task that requires access to that resource will not be released for another 50 microseconds, and it will only take, and I know it will only take you 10 microseconds to use that resource, so that's fine, and there is no blocking. Or the scheduler will say, no, you may not access the resource because there's a high priority task due to execute that will require access to that resource before you have finished with it. So the end result is that there is no blocking of the high priority task in a TT design. And again, that's not magical. It's not based on specific technology to my organization or anything particular that. It's simply the fact that we know in advance when the particular tasks are going to run. Okay, so the next one, what's the minimum frequency allowed? I'm not quite sure I understand that. So typically, the starting point for most systems, many aerospace designs run with 25 millisecond ticks, tick intervals. Most designs run with 1 microsecond tick interval. That may answer some of your questions there. So I hope that's sort of answering that. So that is the time slice period and possibly the answer about the minimum frequency as well. I hope that answers those questions. So how do we ensure that the ticks we produce will always be on time when the machines are working for 10 years or more? Okay, so that's a fair question. So essentially, there are two parts to that. The systems do continual self-monitoring. So essentially it will be checking everything. So typically what our systems do is they perform a reset and a set of self-tests every few minutes, sometimes once an hour, sometimes more frequently than that, during their operation. And they perform various self-tests. And if they fail one of the self-tests, then the system will enter a safe state and will put on a maintenance required light. So the key thing is that our requirements in order are it will operate safely. And the second requirement is that it will operate reliably. So our goal is to ensure that for the 10-year operating life, the system operates safely, or if it cannot continue to operate safely, it shuts down. So I hope that that's an attempt to answer your question. So essentially, we're performing self-monitoring of the design continuously to ensure that it's able to meet its requirements. And if we can't meet the requirements, then we shut the system down. So the answer to the question from Geno Dave, on what basis is it decided that for a particular tick, these two tasks are going to run? Okay, that's another fair question. So typically you will choose the sequencing of the task depending on what the particular tasks are going to do. So you might have task A performing data acquisition before task B runs and processes the data that was gathered in the last task, and possibly, so let's say we have 3 tasks. Task A gathers some data from some sensors, task B performs a PID control algorithm, and task C, based on the calculations from task B, generates a control output from the system. So in that case, we would run the tasks in the sequence A, then B, then C. But it's going to obviously depend on what the particular requirements for the design are. I hope that sort of answers your question. There's no particular magic again to that, and it doesn't really differ very much from a different architecture. So typically so it may help to identify what the tasks are doing. So typically a task is, there are typically 3 kinds of tasks in the design. Tasks that are gathering input data, tasks that are running something like a state machine that some people here will be familiar with, and controlling the overall state of the system. There may be multiple state machines, but there'll be at least one task doing that. And then there will be a task that's controlling the outputs. And again, that will be running periodically. And typically what it will be doing is it will be either changing the state of the outputs, or it will be checking that the outputs are still in the state they were set to the last time the state was changed. So essentially, those are the 3 core types of activities that are performed in most designs. And I believe that's everything.
Sir, Miss Lena Ladge has raised her hand.
Yes, sir. Good evening, sir.
Good evening. What
Hello.
did you want to ask? What did you want to ask?
Audible, sir?
Your voice is cracking a bit. Could you repeat your question?
Yeah. Good evening, sir. Yeah, sir, we are currently. Yeah, sir. Currently, we are researching on heterogeneous multi-core systems, and in which we would be lately working on temperature-based scheduling. So here we would be obtaining the temperature of every core, and then we would be scheduling the task as per the temperature of every core, so that the power consumption is less, and also the temperature can be maintained under the current threshold. So in this regard, I would like your recommendation whether we should be designing the TT triggered based systems or RTOS based systems.
Well, I'd almost never recommend an RTOS based system, but that's just my bias. So I would need to think more about your design. So you're adjusting. You've got a heterogeneous multi-core. So you've got different kinds of cores on your system, and there are some temperature related characteristics to these that I don't fully understand. I would need to understand a lot more about your system to know what I might suggest, whether use of a TT architecture was sensible here or not. If your system is not being used for high reliability or safety related designs, the kind of design constraints that I've suggested in this talk don't apply. There are many successful and happily operating systems that are based on a conventional RTOS or a similar architecture. So there's no fundamental reason not to use these. The approach clearly works. The key challenge is that it's difficult with such designs to provide the evidence that you've met the safety requirements. That's really my central point here. So I'm not trying to suggest that nobody should ever use an RTOS in their designs. and it would depend what the application of your heterogeneous multi-cores was as to the best way forward here. Sorry, that's not a
Okay.
great answer, but I don't know enough about your system really to say much more.
Okay, sir, and can you please suggest any simulator or emulator where we can program or we can design our own scheduler and also test it?
Ma'am, could you just please tell, sorry to interrupt, sir. Could you please tell you're representing a company or you're from some academic sector?
No, sir, I'm a research scholar from SPIT.
Okay, okay. Carry on. Sorry.
Okay, you're local. So I can't recommend a simulation environment. I don't know of one. I perhaps through your colleagues at SPIT, you can make contact and we can perhaps have a chat about this offline. Happy to help if I can.
Okay, sir. Okay, surely.
If I go down the next question in the list, would that be appropriate here? Is there a minimum value of tick interval? In most practical designs, I don't think we've used a tick interval less than about 200 microseconds, simply because the overheads then become too great. But there's no fundamental limit if you've got high levels of processor performance. I hope that sort of answers that. A lot of microcontrollers have more than one timer present. We use multiple timers in practice. So the starting point for the design is that you've got a single timer driving the scheduler. So you've got periodic ticks driving the scheduler. This is to ANKIT data. So we've got a single timer driving the scheduler, but we will use numerous other timers in the system anyway. So I wouldn't suggest you try and use multiple timers to release different tasks. Instead, we would use another timer typically to monitor the task execution time while the task was running. We'd use other timers to give us timeout mechanisms so that, for example, if you access a particular peripheral and the peripheral hangs for some reason, you don't bring the whole system down. Instead, you trap that event and you react accordingly. So we would typically use multiple timers in the system. So the starting point is a single timer for the scheduler, but at the end of the day, we've actually ended up typically using quite a few timers and quite a few mechanisms. So the original, the basic code for a TT scheduler is about 1 A4 page in length when you start, but it becomes a bit longer than that once you've added all the monitoring and checking mechanisms to it.
Any other questions? Oh.
Okay, so that's another good question. So the honest answer is there is no perfect solution. So the basic challenge. So if the question would be, does your IoT system? So this is to Kush Jain, who's raising a question about power dissipation. Yes, I'm sorry, I'm assuming everybody can read the chat. That may not be the case. So Kush Jain has a question about power dissipation, saying that various embedded systems might be used in applications like Internet of Things, etc. And suggesting that effectively waking the system up every millisecond is going to use a lot more power than is necessary in this kind of design, because typically the design might only need to wake up if the user presses an input or something like that. And that's a perfectly valid consideration. I think the question would be, so there are two kinds of basic challenges that we typically face in a safety related system. So let's say the system has a single switch, and when that switch is pressed, the system does something that might be dangerous if not handled correctly. So we need to be able to check the switch has been pressed, and if the switch is pressed and all the conditions are met, we do the dangerous thing. But typically there's a second question, and it's usually much more difficult to check. And the second question is usually, can you be sure that the system will never do the dangerous thing if the switch is not pressed? And meeting the requirements of that second question are much more challenging, because you have to be able to keep precise control and track of the state the system is in all the time while it's running. And you have to monitor for that to make sure that the system is not about to do the dangerous thing when you didn't want it to do this. The kind of question that I would ask, the first question I would ask about this IoT design to Kush Jain would be, what are the safety requirements? So the risk, if you leave the system asleep all the time and it's not waking up to do the checks, then the question is, can you be sure that when you need it to wake up and do something safety related, it's going to do that? And that's the core question. And if that's not a consideration, then I would suggest that you use an event-triggered design. If the power constraints are your real requirement and you only need it to wake up, for example, a TV remote control or something like this, and I don't care if it doesn't change the channel when I want it to do so, then I wouldn't build that TT. But if that TV control was actually controlling a medical design, and I wanted to be confident that the batteries hadn't run out and that it would still be able to turn on the medical device if I press the button when I really need this thing to happen, then I'd probably build it TT. So I'm not trying to argue that TT is the right solution for everything. Try and build a desktop operating system in TT, which has been done, is really not a good idea. Because it doesn't meet the requirements. Essentially, it's a different kind of application with lots of different applications added and removed all the time, a different set of constraints and no safety constraints. So essentially, the answer to your question would be, sorry, I've lost your name off the top, Kush Jain, that you may well be better off building your design using an event-triggered architecture unless it has safety requirements. And in order to answer your question fully, we'd have to sit down, do a safety case for your system, work out what might possibly go wrong if your system didn't wake up when the button was pressed, and we'd take the analysis from there. So the process of designing these kind of systems typically begins with a process that's called a hazard and risk analysis. And that generally means getting the people involved in the system round a table with a whiteboard and looking, saying, okay, what can possibly go wrong with this system? And what are the things that we have to worry about here? And then we work up from that point. And if there are no hazards or risks associated with the system, I don't care how you build it. Doesn't matter. Build it whichever way works for you, would be my answer. So to Adik Mwada, apologies if I've mangled your name. How can we use a graphical language? I don't know the answer to that. So we have not used such a language with these designs. We could probably work out a way of translating ladder type logic into a TT design, but I don't know quite how to do that. I would, yeah. For these designs, we typically use something along the lines of a tick list. We don't use tools. The most complicated tool we use to design these systems, and this scares people, it's Notepad or Notepad++, because most of our designs are represented by a tick list. It's just a list of tasks that run. It just basically says in tick 0, task A runs, then task B runs, and then it just lists what happens in each of the ticks. That is the model. People have created graphical representations of these, etc., but at the end of the day, that is it. Okay, so Dipta Karani, that's another good question. Can we have AI and embedded systems work together? Okay, so AI is a big problem that we're all going to have to deal with. So generally, everything I've been talking about during the course of this afternoon is how do we make our systems highly deterministic? And AI almost has the opposite goal. How do we make our systems adapt and behave in different ways on different days? And I think the honest answer is the world doesn't quite yet know how to deal with that scenario. So the only way I can think of is essentially something like the TT wrapper kind design that I showed you, so that you have your system continually asking the AI-based design questions while the system operates to try and make sure that the AI is not starting to do something bad. Has not decided that kill the humans is the best way to proceed. So you ask it the questions. Now the challenge in that is if the AI gets really complicated is how can you be sure the AI is not lying? But we'll worry about that in the course of the next few years, I think. I don't know enough to Karan Singavi. I don't know anything about MicroPython, sorry. There's no fundamental reason why you have to use C. Is MicroPython interpreted? That causes us some challenges. If it's a compiled language, it matters a bit less exactly what goes on. Yeah, I don't really know the answer to that. I don't know enough about MicroPython to be clear.
It works on the interpreter, sir.
Yeah, so that would in its own right give us some challenges. So essentially we don't use, so it may have dynamic memory allocation, etc. in there, which again presents us with some challenges, and that's something that we tend to avoid in the designs as well. So I think we might have to put your MicroPython in the box with the TT wrapper around it to make me comfortable. So if in doubt, put a wrapper around it. And that wrapper concept doesn't just apply to software or hardware components, it also applies to things like lathes or other electrical equipment, in my view. It's always the same concept. You've got something that might potentially be dangerous and you're putting a monitoring system around it to make sure that nothing bad can happen to the people using the system or in the vicinity of the system. Run out of questions.
Yeah, I think it's over, sir.
I think it's over. Perfect.
Yeah. So last question I would like to ask, one or two non-technical questions.
Yeah.
So there are students also in the audience from our institute. So if someone wants to make a career in the functional safety domain, then what kind of a career path you would like to recommend?
So really, it's a question of finding almost any organization that's involved in safety-related systems, and that's a very wide range of organizations. Graduate with a good degree, some core experience. So functional safety involves both hardware development and software development for the kind of systems I've been talking about. So it could be a degree in electrical and electronic engineering, perhaps it could be a degree or a qualification in software development. And most organizations that I work with have difficulty recruiting good staff. There are lots of openings here, and this area is growing enormously and is going to grow even larger over the course of the next few years. I think Dipti Karani has a key point here. Some understanding of AI may also be useful going forward, because that looks as though that's going to be another factor that will need to be considered. But really, the key bit that we're looking for when we recruit in this area is people who can think outside the box. That's the central core to it. So organizations doing this, the key challenge in the organization is to have a safety culture, which basically means everybody has to think about what might possibly go wrong with the system. So if you want to just be told what to do A, do B, do C on a daily basis in your work, this is probably not for you. What we're looking for people is that can think a little bit outside the box and want to think outside the box. And a question I always ask during interviews is, I say to people, okay, if the system you're developing with us in 2 months' time goes wrong, someone's going to die. And I say, does that scare you or does that excite you? And if that scares you, we probably don't want you here. If that excites you, well, we're probably the right kind of organization for you. Come and join us. Yeah.
Okay, yeah. Sir, my last question would be, your major work is in European countries. Any plans, any expansion plans you are thinking of in the Asia, particularly in India? It's a big country and a lot of scope is there. So any thought on that or any?
We've had various discussions about projects in India over the last year or so, even in the last few months, a big potential rail project in India. So we would be very happy. Haven't yet done a large project in India, but we are already working with one large organization in India, and that may develop into a big project. So we'd be very happy to work in India. It's an exciting country. It's a country I visited many times, and I look forward to coming back when the world becomes a bit more normal again.
So thank you, sir. Thank you so much. Bhagat sir, sir, I would like to.
Yes, sir.
Yeah, please. You are right. Sir, thank you very much, Dr. Michael Pond, for joining this session. I know you are very busy, but you accepted our invitation. Thanks a lot for that. You have given us a very good insights about time-triggered embedded systems. No RTOS, no Linux Windows, very limited use of interrupts was a kind of an insight that you have given. You have provided the complete perspective of what exactly time-triggered software architecture is about and how it is different as compared to the conventional RTOS architectures. You have given the insights about the prototyping and also about the compliant systems, how one can reduce the gap between the prototype and making the compliant systems to an extent of 6 months. That's very great to know about it. Then you have also explained about the model build monitor kind of a methodology. And you have given a simple example of a scheduler that was great to see from you. And you also explained about the time-triggered platforms for the fail-safe systems and time-triggered wrappers. And MISRA-C, we are nowadays training ourselves about the MISRA-C standards, and to know from your mouth that MISRA-C is definitely is useful in the safety critical systems is great to know about it. And you have also given a very good example about the key design issues. I do remember that example on your slide about that there could be a requirement that only 50% of the load should be there during the normal time. So great to know about these insights, sir. Thank you very much. Thanks a lot. You accepted this invitation. And I would personally like to thank you for association with SPIT from last 2 years. You accepted our request for having an MOU, and we had a great courses in our institution from last 2 years in association with the micro devices, and with your kind permission, we had those courses, and our students are doing a fantastic job. Those who have completed those courses and working in industry, they still remember the courses offered by micro device and under your guidance. So thank you for not only for joining today, but thanks a lot for all those courses. And we are also looking forward for this association in future with you. We will definitely get back to you, and I hope you don't mind whenever we connect to you, sir. Kindly accept this as a token of appreciation in a virtual way, virtual memento, we would say.
Perfect.
So yeah, thanks a lot. Thank you joining, and we had a really great session, and much more greater than that is a question answer session. The questions were also excellent. I would love to see those questions coming from the audience. And the way you answered was also very, very great. It was really an excellent thing.
1 minute.
Yeah. So thank you, sir. Thanks a lot. Thank you very much.
It's a pleasure. Thank you very much for inviting me. Thank you. And I hope the rest of the conference, the rest of the tutorial session today goes well, and the rest of the conference goes well. Thank you very much.
Yeah, sir. Yeah.
Thank you very much for having joined this conference. It was a pleasure.
Thank you. Bye.
So,
thank you.
Yeah, so participants, we will have now, I think we will take a 10 minutes break, Govind sir.
Yes. Okay. Not a problem.
Yeah, we will take a 10 minutes break, and you remain connected. Meet will be there. So after 10 minutes, we'll come back and Govind sir will take over. And then don't forget, at the end, you will have two things to be done. One is giving a quiz the way we ran in the morning. And now it will be little bit more technical. And second is you will have to complete the feedback form at the end of the session. Okay. And thank you very much for all your questions. Great session. Break of 10 minutes. Reena madam. Reena madam. Hello, madam. Hello, madam. आपका आवाज नहीं आ रहा है. हाँ मैडम.
हाँ सर बोलिए.
हाँ हाँ, 1 मिनट के लिए मुझे वो होस्ट का राइट दीजिए. आई विल ट्रांसफर द फाइल टू डाउनलोड इन द चैट बॉक्स, द प्रेजेंटेशन ऑफ Dr. Michael Pond, so that everybody can download it directly. Yes, na? So I need not send it through mail, etc. आपसे host का अच्छा 1 मिनट. I got it. It is there. Just a minute, madam.
हाँ सर.
Let it be. I think it's there. Just a minute. I was not able to see it, but I could see it now.
Shall we start, sir?
Just a minute. So everyone, you can see your chat box. I have uploaded the handouts given by Dr. Michael Pond of his session. You can download. It's there in the chat box. I think you should be able to download. Sir Govind sir, can you see in the chat box?
Yes. I am.
Is it downloadable?
That's what I'm doing. Let me just do it. Let me check.
File madam mentioned yes sir. That means, madam, but you are able to download. I just want to know. File madam.
Yes, I can download. I downloaded.
Okay, done.
Done.
Yeah. So hand over to you, sir, Govind sir.
Yeah.
So participants, you can download this Dr. Michael Pond's presentation from chat box. I'm not going to send it through email. All those who were present in the session, they are still there, so you can download it.
Yeah.
Go ahead, sir.
Yeah. Okay. Yeah. So welcome back. It's time to now move on. And I hope all of you enjoyed that session. That was a really, really informative session. And every time I listen to these sessions from Dr. Michael J. Pond, there is something new that I always get to.
Sir, little louder. Mic or headphone or something like that.
I am. Can you hear me now, sir?
Yeah. Now, fine.
So basically, these sessions of Dr. Michael J. Pond are extremely informative, and every time that I hear these sessions out, I really learn some new things out of it. So it was really a great opportunity for all of us to be actually hearing from the creator of this technology. Yeah. So let's start off now. I'll be sharing my screen with you. Let's continue from where we left. Yeah. I hope you can see my screen. Reading switches.
Yes.
Yeah. Okay.
Sir, audio फिर से आप थोड़ा adjust कीजिए ना.
Is it okay?
This is okay.
Yeah. So we are going to look at how to read switches. This is a very critical part of an embedded system. So let's start off, and we'll see some code associated with this as well. So now you can see there are different types of switches. You can see different pictures of different kinds of switches over here. The only reason for putting so many pictures over here is, whenever you're designing such systems, the choice of a switch is also very important. You just cannot pick up any switch and put it up in any system. The switches should be, they should be able to speak out what state they are into and what kind of a system you're going to design. So it's not just that you put up any switch anywhere and you're on with it. So selection of the switch is important, and apart that is the first part of it. Like for example, you are into a safety a door of say a nuclear reactor. You cannot have just an on-off switch over there. The switch should be such that it indicates the state of that door, so that accidentally somebody does not put that door into an unwanted state, just not knowing what state the switch is in. So it should be an indicative switch, clearly marking whether the door is engaged or what is the state of the door. It should really speak it out. So choose your switch based on what kind of application you have. That is very important. And if you see these embedded systems that we use, their most important interface is a switch. Without a switch, you will rarely find an embedded system. Like from the basic remote controller to a garage door to a most sophisticated aircraft autopilot system. If you see the cockpit of an airplane, it's full of different kinds of switches with some push buttons, with some extremely stop switch kind of switches, with some on-off switches. Different types of switches are there. So whatever the system you create, you need to be able to create a reliable switch interface. This is where the safety starts first. So when it comes to an 8051, it's a pretty straightforward code. We are still not into the actual time-triggered architectures. We have still not seen that. But here we are putting up a simple, the switch reading code. So first we are making the port 1 a readable port by putting that FF. And then we are actually copying the value of the port to the port 1 value variable. And then we are copying that to port 2. So we are actually copying something from port 1 to port 2. That is what this thing is doing really. So nothing different or nothing very special. It's the routine that we generally do with any kind of an embedded system design. And as most of you know that you may need a pull-up resistor, and it really depends upon how the internal port pins of that microcontroller are configured. So when the switch is open, it has no impact on the port pin. An internal resistor or port pulls up the pin to the supply voltage, typically around 5 volts to 3.3 volts, depending upon what kind of power rail is used. And if we read the pin, we will see the value 1 whenever you have that port pin raised or pulled up. And when the switch is closed, the pin voltage would be 0. So if we read the pin, we'll see the value as 0. This is the normal operation with a pull-up resistor. So if you visualize your pull-up resistors, this is how it would really look in reality. You can imagine this to be like a spring with a pull-up. So whenever you press the spring or the button, it's like some tension is generated. And when you release that external force, it goes back to its original. So without the pull-up, this is what you would generally see. So that is the reason you need the pull-up resistors with many of the port pins in many of the microcontrollers that you're going to use. And how do you do a pull-up? With the general 10K ohm resistor that you just tie between the VCC and the switch pin. Now comes the debouncing concept. And we all know that mechanical switches experience this behavior. And you really need to take care of this bounce by debouncing the switch. Nothing new over here. And if you don't take care of the bouncing, you will see something like this. That is, you can see that the microcontroller will read these transitions at the press and the release of the switch. So you need to really debounce the switch. So what actually is the implication of this is when you are not, if you don't deal with that switch bounce, rather than reading an A from a keypad, you would actually be reading A, say if you're pressing the key A, and counting the number of times that a switch is pressed becomes extremely difficult. So if a switch is depressed once and then released sometime later, the bounce may make it appear as if the switch has been pressed again at the time of release. So we really need to be extra cautious when we are dealing with switch or switches that are connected to the microcontroller pins. So how do you deal with a switch bounce? A very simple algorithm is in place always. So what do? We read the port pin. And if we think that we have detected a switch depression, we wait for around 20 milliseconds. That's the debounce period. And then we really, okay. And then we read the pin again. And if the second reading, that is after the 20 milliseconds, what reading you take, if that confirms to the first reading, we assume that the switch has been depressed. So you have actually debounced the switch by waiting for about 20 milliseconds. 20 to 50 milliseconds is a good debounce period. And what this really translates to physically is, this debounce period should be greater than or equal to the mechanical bounce period of the switch. So if you have a switch whose data sheet is available, you can see what is the mechanical bounce period of the switch. And based on that, you can decide on the debounce period that you really need to employ. So it's a pretty simple algorithm. Read the port pin, wait for 20 milliseconds, and read the port pin again. And if the first and the second reading confirm, you have a valid switch press. Now, how does this translate into real code that we will see? So the switch reading code that we'll see would be more than adequate for applications where we are driving a motor while a switch is pressed, or switch on a light while a switch is pressed, or activate a pump while a switch is pressed. So that is a pretty good, a starting point. So for example, if at all we want to drive a motor while a switch is pressed, if the safety guard is not in place, don't turn the motor. Instead, sound a buzzer for 2 seconds. So that is how we are going to make use of the switch. So switch on the light while a switch is pressed. To save power, ignore request to turn on the light during the daylight hours. So that is the condition. That means it will just ensure that if there is a daylight, the lights would be turned off. And activate a pump while a switch is pressed. So if the main water reservoir is below around 300 liters, we do not start the main pump. Instead, we start the reserve pump and draw the water from the emergency tank. So basically, these are simple, switch applications that we generally see in our day-to-day activities. The other activity that you generally need to have is count the switch presses. So with the simple code, of course, we'll see the code in Keil. With the simple code that we generally employ, like the algorithm that we spoke of a little bit in the previous slide, there can be problems with that code whenever a switch is pressed for a longer period than the debounce interval. That means you're holding down the switch and not releasing it. This is a concern because in many cases, users will press switches for at least 500 milliseconds. That means whenever you do a switch press, any human, the switch is pressed generally for about 500 milliseconds. That's a natural human tendency. Or until you receive a feedback, that is some kind of an audio tone that you receive that a switch is pressed. So as a result, instead of typing a hello, you may just type something like this, which is not a real, really true input that you were expecting to give to the system. So such kind of, if you need to really take care of all this, you really need to be sure about how the code for switch press detection is written. So the consequences of this is, this could also be used to actually count the number of switch presses that you're going to do. Okay, so the switch interface code that we are going to see in a little while from now will allow us to do two things. One, to perform an activity while the switch is depressed, and to respond to the fact that the user has pressed and then released the switch. So basically, we are going to look at two things, that we perform an activity when the switch is depressed, and to respond to the fact that the user has pressed and then released the switch. In both cases, we should have debounced the switch in software. Okay, so now let's get into that code, because that is how you would really get to see what I'm really saying. So let's open it up. Okay. Yeah. So yeah, I'll just share this screen with you now. Let me just open it up. Yeah. So I hope this screen is visible to all. Can you see this?
Yes, sir.
Great. Okay. So now we have a switch press code over here. And as I said in the earlier part of this session, we would be actually having the constants and the values defined so that the portability issues can be taken care of. So we have the port 3, that is actually we are going to use output port as the value instead of port 3 P3, and switch pin would be used for P1 port 1 pin 0. So our switch is connected at port 1 pin 0 and our output port is port 3. So these are a bunch of different functions that we have, like initialization for the switch. Then we're getting the input, whether the switch is pressed with a debounce period. Then what is the display the the status of the switch, and an update function for the switch, and a delay loop for ensuring that we employ the debounce period. So let's see how this all clubs together. We have our main function, and we have created one state variable, that is switch state. We call our initialization functions like switch init and display switch status init. What do we have in this? So in switch init, we are saying that we are using this pin for the input, that is the switch pin. And in display switch status, we are actually putting up what we are going to show up on the output port. So this is actually going to show us the output port, and this would this function switch get input is actually going to take up the debounce period that we are going to give, and it's actually going to debounce the switch. So the debouncing is going to be done here, and finally this will actually put the value on the output port, whatever is the output that based on the switch presses that we do. And this is the delay loop that we are going to use for generating the debounce period of 30 milliseconds. So to start off with, the system initializes the switch. We saw that it will initialize the initial output of that output port, and then we call this function switch get input, and we are passing a value 30. That means we are going to debounce the switch for 30 milliseconds. So it comes over here, and what it does is it first checks if the switch pin is 0. That means if the switch is pressed, and then you would call the delay loop for about 30 milliseconds. Mind you, this is still a software delay loop. There is no hardware timer involved over here. So it's going to debounce the switch for 30 milliseconds, and then it's again going to check whether the switch pin is still 0. If it is still 0, that means we have a valid switch press, and we say switch pressed, the constant switch pressed is stored in the return value, and we return the value. So this goes back over here, and the switch state is now switch pressed. So that is taken as an input by the display switch status update function. So if the switch is pressed, this function over here will come and check if the switch status is switch pressed. If it is pressed, we will toggle the output port to 0F. But if it is not pressed, we'll toggle it back to F0. So this is how we have actually debounced the switch. Nothing new over here. So this is straight simple debouncing. And this is the algorithm that we really saw in theory being implemented over here. So let's just quickly run this. and see whether we get the desired output. So we have our input over here on this on this pin over here, and you can see it's toggling. That means whenever I'm pressing the switch, it's actually toggling, and things are working fine. There is no issue here. I hope this clears up the basic understanding of how to actually implement a switch interface. Now let's move a little bit further with a different code. So I'll just open up some other code now. Let me just do that. And yeah. Now, before we actually dive into the code that I'm going to show you now, I'll just show you a snapshot of it, and then we will go into the details, because now things have started becoming slightly different. Of course, still it's in the, we are not into that time triggered zone. But if you see on the left-hand side, there are a host of different files that we have created over here. And most importantly, if you see this program, it's again about switch presses and counting of how many times the switch was pressed. But to write this type of a code, we have created an absolutely modular structure. So we have our main functions like the C functions. You can see we have the main.c, we have a display count.c, we have a delay timer 0.c and switch wait timeout.c. So there are a host of different C functions, and associated with them are a host of H files, the header files. You can see these. I'm clicking over here. Now, what is the purpose of doing this? Why have we created this kind of a modular structure? So to really understand this, we have to really first see what is the basic idea behind doing such kind of a design. So I'll need to share my next slides with you. So I'll just open up the slides. Yeah. So I hope you can see my slides now. So here we are saying we are adding structure to the code. Now that same switch program with some more modifications in it, we are going to see in that that updated code that I just showed you. It was just a snapshot, but to understand what we have done over there, we need to go through these slides a little bit. So what we are going to see is we'll describe how to use object-oriented style of programming with C programs, allowing the creation of libraries of code that can be easily adapted for use in different embedded projects. So we are going to create, as I said, we need to really create modular code so that we can have a repository or a library of the codes that we write. Then we will see why we need those project header files. It actually encapsulates the key aspects of the hardware environment, such as the type of the processor to be used, the oscillator frequency, the number of oscillator cycles. Of course, this is relevant to a little bit 8051. So it will actually help us to understand these things. So we are actually going to see one more thing. We will also describe how to create the port header file. So this brings all the details of the port access for the whole system, like the project header. This helps during porting. So basically what I said was we create a project header, we create a port header, and we create a repository of the code. So this is how we are going to actually structure our code into our project, rather than having a flat file, which is what many a times people do, and generally people write it that way. But that's not a good way of doing it, especially when you're working with such safety critical designs like what Dr. Pont was talking about. So how do we go about it? Now, everybody knows C is not an object-oriented programming language. It's certainly not. But you can certainly pick up the ideas of object-oriented programming languages and use those ideas over here to make that modularization. And you can do this using file-based classes and without imposing any significant memory or CPU load. So it's not going to add to your CPU load. In fact, it's going to make your code more elegant and readable and more maintainable and more deterministic, so that errors are minimized while the code is being maintained or updated or upgraded. So instead of having all the programming in one single source file, we break it up into different C files. Like, for example, if I have serial port related code that I want to incorporate into my system, I want to incorporate switch related code, and I want to incorporate the scheduler. So I will have different C files doing different things and an associated header file, that is the H file, with that C file. So this is how you should really start off with any project. When you start off with a project, when you try to make it, then you can use the typedef keyword, which is a very useful keyword in C programming language that allows us to create user-defined data types or aliases to the data types, which will simplify your life. And especially if you are doing, if you plan to port it to different families like 16-bit families, 32-bit families, or for that matter, even 64-bit families or 8-bit families. So what we would do is something like this T word temperature rather than unsigned int temperature. So this T word is actually an alias for unsigned int. So using typedef, you can do that, and it will greatly simplify your life when it comes to porting the code to a different family altogether. So the main reason for using these typedef statements is to simplify and promote the use of unsigned data types, and it makes sense to use unsigned data types in most of your designs. The 8051 does not support, it doesn't support signed arithmetic, and extra code is really required to manipulate signed data. So if you do that, it's certainly going to reduce the speed and will increase the program size, which is not a good, not a good idea to just go on writing codes. Multiple lines of code. If certain things can be done in 5 lines of code, there's no point in writing 20 lines and just increasing the code base and increasing the chances of errors. So use of bitwise operators generally makes sense only when unsigned data types are used. So use of typedef kind of variables reduces the likelihood that programmers will inadvertently apply these operators to signed data. So if it is already defined in your header file, something like this, there is no chance that some programmer may inadvertently use an unsigned data type or even a wrong data type. For example, if at all you want a word kind of data and you have assigned a byte, it's going to really lose, you are going to lose information in that particular variable. So these are some kind of, very critical design aspects which can give rise to some errors in the long run. So you can safeguard yourself by doing such things. So finally, as in the desktop programming, use the typedef keyword. In this way, we can make it easier to adapt the code for use on different processors. So this makes your code extremely portable, which is very essential. Next, there are multiple interrupts in most of the processor families that you can use. So you can really have, especially in 8051, you have interrupts which are linked to the vector number, the interrupt vector number. So rather than using those numbers, you can give names to your vector numbers like this, so that you know what that 1 is for, what that 0 is for, or what that 2 is for. So basically, you give the names of the interrupts and attach them to the vector numbers that you have, so that it becomes easier for the readability is improved, and that reduces chances of errors. So rather than using 135, you would rather, you're better off using names for those interrupts. So now, why do we need to use a project header? It will make your code more readable. And most importantly, developers, if it's a distributed design exercise, that means different developers are sitting in different locations, different parts of the world and working on a project. So readability becomes easier if it's structured like this. And programmers would know where to find key information, such as the model of the microcontroller, what is the oscillator frequency used, and so on and so forth. The use of project header can make your code portable, because you are actually placing microcontroller dependent data. This is very important. Microcontroller dependent data, meaning every microcontroller has got different kinds of ports, different timers, different names for the timers. So if you can place all this key information in one place, just modifying that one single file is easier, and then your rest of the files will pick up the information from this file and work on it, rather than keeping it scattered across different files the way I showed it to you earlier. So when you have names given to your different values, it becomes easier to actually use those names instead of those values, and that increases the portability of your code. So if you change the processor or the oscillator used, then in many cases you'll need to only make changes to the project header, and not you don't need to search through your code as to where you have hard coded the frequency of the clock frequency in your code. So never do that. Don't hard code values. Instead, put them in one project header, so that once you make a change over there, it reflects across your entire project. So now what is the next file that I would be really interested in? It's the port header file. So this was the project header. This is the port header, port.h is generally what we call it. And here we will put all the port related information that you're going to use in particular in a particular project in one place. Like over here, we have said that we have 3 different files: file A, file B, file C. In file A, we have kept say port 3, pin 2 related data. In file B, I have kept port 0 related data. And in file C, I have kept port 2, pin 7 data. So all these port related requirements over here, you see they are scattered across files. Now, this is a potential source of error. Rather than having this in separate files, or I have seen people, whenever a requirement comes during their coding journey, whenever a requirement comes for using a particular peripheral, they'll just initialize the peripheral right over there and start using it, without even thinking that if there is another programmer who would be working on that particular project somewhere else, he would not know what port pins you have used. So if your port accesses or port pin related data or port related data is in one centralized location, it always helps, rather than having something like this. So all these different port related information is scattered across different files. Don't do that. Extremely bad practice. Instead, what you can do, you can have a port.h file and put all that information in one place. And as I said, always give some names, some relevant names to your port and port pins, rather than just having the standard register definition names that are declared by the manufacturer in the microcontroller H files. So give them some relevant names and put them in one place, generally a port.h file. That's the best way to do it. Then comes some important aspects about accessibility of functions, constants, variables. So here we can really think of, our object-oriented programming concepts, really. So what is public? Functions, constants, variables declared or defined in the header file. Any C file that hash includes the header file can see these constants, variables, and functions. So assume that you have created some functions and constants, and you have some variables that you have put in an H file. And in any C file that you're going to include that H file, all these functions, constants, variables will be visible to that C file. So that makes them public automatically. So certain number of variables defined in the source file, stored in the memory as long as we are within the scope of the block in which they are defined. So, and you should know what you want to make public, what you want to make private. You cannot have everything stored in an H file and then use that H file across and it's available throughout your project. If it's not needed, don't put it, don't make it public. That could be chances of potential errors over there if you do that. Then comes the private variables, functions, or constants. Now these private functions or variables that we are going to talk about, they will have their prototypes within the C file, and use the static keyword when declaring these rather than putting them up in that H file. So now they are only visible to the C file in which they are declared or defined. And use static keyword also when you're using your variables and constants defined within the C file. They are invisible outside that C file then. So you have achieved, information hiding kind of a concept that you have in object-oriented programming languages. Then you have one more keyword. It's the extern keyword, the static and extern. So what these two keywords actually do is they allow you to control function and data encapsulation. That's their function basically. So a static variable, which is local to the block in which it is defined, its value persists between function calls. So if you have a variable, its value will persist between numerous function calls. You make it static. Now an external variable, it has got a global scope. It remains as long as the program execution does not come to an end. So that is how an external variable can be used. So you should know what you really need to, how you really need to use your functions or your constants, or for that matter, your variables, where you want to put them. You want to put them in the C file or the H file. It all depends upon your use case. You just cannot haphazardly have it anywhere, because then it would be available to some files where it should really not be available. So this is why we need to do that kind of, structuring of the code, as I just showed you in that snapshot. We'll go to that code in a little while. But why you need to do it and how we have achieved it is what I was really trying to show you through these slides. So now it's time to really look at it in practice. So remember one simple thing. This is what you really need to remember. Create C files and an associated H file, and then think whether you really need to give access to the entire project or to a specific, it should be specific to a C file, or it should be used in multiple C files, how you want your variables, constants, or functions to be used. And doing this does not affect performance. Okay. So with that in mind, let's see that code once again. So I'll just stop this and let me share this now. Okay. I hope you can see my Keel code, everyone. Okay. So now you can see there are multiple includes over here. Main.h, port.h, switch wait timeout l.h, display count.h. Now, what are these H files? Let's have a look at them. If I just click on the H file, here we are having a conditional compilation in place. If not defined, define, and whatever that is there after that define, we are creating the function prototypes. Now, these two functions, that is the count init and count update, it has been put in this display count.h. So whichever C file in which this display count.h is included, all these things would be available over there. So in a way, they become global. So wherever you are going to include this, it's going to be available over there. And what this conditional compilation is really doing is it says that if it is already defined, if it is not defined, define it. But if it is already defined, just leave it. Don't do it again. So there is no redefinition of your functions or your variables that you're going to put over here. So that is this now display count.h is actually associated with this display count.c. So if I open that display count.c, you can see those functions would be over here. The implementation of the function is over here. Okay. So now let's start off with the main.c file. This is our starting point. So I just showed you how that I just picked up a random file and I showed you what that really means. So now we have included all these H files. So now what is there in this main.h? So I am in main.c. What is there in main.h? The main.h file, if you see, has included the main register definitions that would be used by that microcontroller. It is defining the oscillator frequency. So the advantage of doing this is whenever you're doing some calculations in your code, rather than actually hard coding this value over there, you use an alias or a name for it and use that name in place of the hard coded value. So anytime that you want to change your oscillator frequency, you just make a change over here and not in your, don't keep searching in the entire code. And this is only exclusive to 8051 because you have numerous 8051s available that use different oscillators, oscillator cycles per instruction. Some of them use 6, some of them use 4, some of them use 1. And this would be essential in doing calculations. So we have even defined that over here. So this is very much my main.h file. And in main.c, I have my actual implementation of the code. So when I come to this particular file, what is there in the main function? The initialization, the switch init function, the display count init function, and then we are just checking in this while in this super loop whether the switch was pressed. And if it was really pressed, we just keep counting the switch presses. Okay, and then we show that we update it on some kind of a display mechanism. Generally, in this case, we are just using LEDs. So this is pretty much what we are doing over here. Now, if you see the switch init, display count init, this switch init function is actually going to be a part of my switch code, and this display count init is actually going to be a part of my display code. So let's see now what is that there in that display count.c. If you see, it's having the original init function of the display count and the display count update function. And observe that we are using a t byte over here because we have already defined what t byte is, rather than actually using the unsigned int kind of the keyword. So this makes it portable. Going back to this, these functions are defined in display count.c. Then if I see the switch wait timeout file, this is also a C file. Over here, you can see I have the switch init. I have the switch get input function. I am going to call the delay timer 0 wait function. So this is actually, we are going to use the timer over here. So if I'm going to use that delay T0, I need to have that H function so that I can use that file over here. So this is going to allow me to have any file, any C file that is a public file, because it's put in that H file, to be accessible in any file. So this makes my code perfectly modular, and I can have total control on what a file sees and what a file doesn't. Okay, so this makes it more of a, an object oriented style of a structure. If I just close these things, you'll see the main C file. These are the only main C files, and all the H files associated with those C files are actually then, after compilation, you can see that they have come underneath the main files where they are used actually. So now let's understand what's happening in this code. First, let's run this. Okay. And now I'm running this. So if at all, I'm going to press this. This is the switch over here. I'm going to press the switch. Just keep an eye on this port. This is switch press 1. Switch press 2. So it's 1 0. That's 2. 3 0 1 1. 4 1 0 0. 5 1 0 1. 6 1 1 0. 7. So I have actually counted the switch 7 times. So this is the switch press count that we did earlier. But now over here, what we have done is we have ensured that we have broken up this code into a modular code. That is the difference. And it's perfectly counting the number of switches that I have pressed over here. There is no problem whatsoever that you can see in this code. It's absolutely bang on. But now I should really show you some problem that this code would have had if I had not done some kind of a special arrangement that I have done with the switch get input. So what is the switch get input really is, you can see over here in the main.c file, switch get input. This function is actually detecting the switch press and it's debouncing the switch as well. So if I go to this function, this is the function. It has a debounce period. It takes 30 as the debounce period. And to start off with, we are saying the switch is not pressed. The return value is that. And we have introduced one timeout loop over here. Let us understand. Let's forget the timeout for the time being. What we saw earlier was we were saying that if the switch is pressed, then debounce it for 30 milliseconds. And here we are using the timer 0. So we are not actually using the software delay loop. So we are saying that debounce the switch using timer 0 for 30 milliseconds. So it waits over here for that 30 milliseconds to elapse. Once that is done, it comes back again and checks. If the switch is pressed, that means the first reading and the second reading, if they confirm, then you have a valid switch press. But now we are counting switch presses over here. Remember that. So what is an actual switch press? A press and a release, right? So I really need to check that the switch, while the switch is pressed, I don't count. I will count only when the switch is released. So I will write something like, something like this. 1 minute. This is what I'm going to write, right? While switch pin is 0. While the switch pin is 0. That means while the switch is pressed. Wait over here. Is this okay? Are you getting this, everyone? Anybody has any kind of reservations on this statement? Is this statement correct? This is what you would have generally done. I have uncommented it now. While switch pin is 0. Is it fine? I want somebody to just say something about this quickly. One minute, let me just check. Okay. It will count multiple times. No, if switches kept press, code will be stuck there. Okay. That's right. So I hope everybody can see the chat boxes. Some answers have come up over there. And they are right, most of them, whatever that they have said. If at all I keep this statement, it's a while statement. And while switch pin is 0, that means while true. While true means your code will hang in over there while the statement is true. And it's a potentially catastrophic statement. Never should you write something like this. And many of the data sheets really have such kind of code. But in safety critical coding, this is a very, very deadly scenario. The reason for this is your code will be hanging over there till the statement becomes false. What if the switch is not released? Will it ever become false? No. It will always be true. So if it is always true, the next lines in your code will never be executed. It's like, imagine you putting up a chewing gum on an elevator switch and just running away from there. What happens? if it is not properly designed, that switch button would be pressed and no other floor would be able to register their request for the elevator. So how do you come around with this? You need to have some kind of a timeout mechanism over here, so that after a certain amount of time, even if this condition never becomes false, you should be able to break this loop. So for that, you will have a timeout that could be just a counting value, a simple counting value, or to make it even more safer, you can employ a timer right over there. So whenever the timer overflows, this loop becomes false and you break out from there. And this could be a condition, not a malicious user. It could be a condition where the switch itself fails and it's always remaining in that true state. So what we can do is we can really have something like this. This is what I really had earlier. So what we are doing effectively over here is we are saying that if the switch pin is pressed, while it is pressed, stay there. And at the same time, we have one timeout loop. And what is this timeout loop? You can see I have some constant that I have defined over here, and there is some value that has been assigned to it. So if I just go to the this definition of this particular timeout loop, you can see I have specified some value over here. And these values have come out of simulations. So what happens over here is, when it comes in over here, the timeout loop starts counting. And it will count till the point of time that it doesn't overflow. The moment it overflows, it becomes 0 and this AND condition becomes false. The moment it becomes false, one of the condition being false, the while loop breaks. And your code moves on to the next line. If this had not been there, that is, if this condition was just there, then this could have been an extremely catastrophic statement, and this could even bring an airplane down with just one line of code. If this doesn't come out of that, of that line, it's stuck over there endlessly. So when you're writing such kind of programs, now this is a simple switch program that I have shown you, but look at the implications of just one line over here. I hope everybody has got the essence of this line. If you have, just give me a thumbs up, because I have just shown you one aspect of safety coding. Yeah, I'm getting some. Okay. So basically, when you are writing such kind of code, you have to take extra care. Otherwise, you are in for big trouble. So this timeout is nothing but it's just counting the number. That's it. Or you can very well implement a timer as well. And over here, we are actually using a timer to debounce the switch. So this timer over here, delay timer 0, it's actually in that C file, that is delay timer 0. And you can see that we have initialized the timer. We have made the timer, all the timer configuration has been done over here. And one more thing that you can see over here, we have some values over here: preload 01H, preload 01L. So what we are doing is, what is the value that you need to load into the timer? We are doing the calculations for the timer reload values dynamically on the fly. And the reason for that is, if at all in the future I change the oscillator clock frequency and I change to a different processor that has different oscillations per instruction, my calculations would be done dynamically on the fly, and that would be substituted in the timers high and low. This makes my code extremely portable and efficient for future upgrades. So I need not worry about doing these calculations manually and hard coding the value. See, there is no hard coding anywhere. If you see this, it's all dynamically done. And the reason for this is this minimizes errors. If you had hard coded this and the programmer would have forgotten to really update this after a change in the oscillator clock frequency, or for that matter, you know, the oscillations per instruction, this would have been invitation to all sorts of problems and all sorts of errors, and your system would really fail miserably. And the reason is just that the programmer forgot to update these values if they were hard coded. Now they are not hard coded. You just make the change in one place and it's applicable everywhere. So what I'm trying to show you is these are some of the better coding practices that you need to follow. Okay. 1 minute. I think I have some question over here. What is that? If we define timeout with different values, the time of getting out of the while condition will be different. Is it normal according to applications? Yes. Now, somebody has asked this question. It was a good question. If we define timeout with different values, the time of getting out of the while condition will be different. Is it normal according to the application? Now, see, the timeout value that you're going to employ over here. Yeah, the timeout. Okay. So the timeout value that has been set up over here, this has to be carefully done. Now, if as Dr. Pond said, there are tick lists that you're going to make. How I mean, what particular task is going to run at what tick. If you have a timeout that is greater than the tick time, you are in for trouble. So this timeout should also be within the tick time. Otherwise, your this would never work. It would give you all sorts of problems because it has to finish the task within a particular tick. So these calculations are to be done when you are actually modeling the system, like how much amount of timeout do you need to give. Otherwise, it may so happen that this task may just run for a time period that is not intended for this particular task to run. So if you want this to be within those limits, you have to even work out this timeout loop to a value whereby no matter what, that is your worst case execution time of this particular task. So make the timeout loop such that it reflects the worst case execution of the task, so that if the switch pin is released well in time, no issues. But if it is not released for some issue like a switch failure or some malicious user just keeping the switch pin pressed, the timeout loop will break this loop in that specified period and not extend it beyond that. So that I hope that answers your question. I could not see your name, but I hope that answers your question. Anything else that anybody has to ask on this? Is this thing very clear? Are we good to go further? So now that pretty much sums up the switch interface. So whenever you are working with switches, you have to take this care. This is one, place where your code can really fail. And the switch interface is the most common one, along with debouncing. It was not just about debouncing. Debouncing everybody does, but the part of the switch that that switch code that I really showed you, that was the most critical aspect of this code, where you can really face problems, right? So now let's move on further. Okay. So let me see. Now we are going into the next part. We are still not into, I'll just show you the time triggered architecture now. Okay. Just a minute. Let me share the screen with you. Okay. Okay, fine. Now comes the critical part. Where are my... Okay, I hope the... Okay, I hope this is visible to all. So now we come to the most important aspect, controlling execution in time. Till now, we had seen the Superloop architectures, and we'll see some more over here. And then we will see the sense of a time-triggered embedded system. So this is our this is what we really started off with in the morning, and we saw what the Superloop architecture was really, and the real problem that we have over here is we really can't control the execution time of the function x. So how do we like what are the implications of this, or how do we really ensure that x runs at the right time? So, and why do we need it in first place? The correct trigger of the task at the correct time. So many a times the requirements for an embedded project would be, we have to measure the speed of the vehicle at around 0.5 second interval. So this is a requirement of a system in general. Then the display in the car should be refreshed 40 times a second. Then a new control setting must be calculated every 0.5 seconds. The keypad must be scanned every 200 milliseconds. The sensors must be sampled once per second. So these are some of the requirements of the system, and they are driven by time. So this architecture will certainly not allow me to do that effectively and accurately. So we need to find out some ways. Of course, you can do it, but then there are issues involved in that. We will see that. Now we have this simple system. Here we call our initialization routine for initializing the system. You're not interested. Just imagine it's a black box. The real challenge is now in the super loop. We have this X function which runs. And then once that X function finishes, we call the delay loop function for 50 milliseconds. So this delay, assume that it's a hardware delay, not even software delay, because when I'm saying that it's a hardware delay, it would be accurate. So we have a hardware delay of say 50 milliseconds. Now, can anybody really tell me that X would be called every time exactly at 50 milliseconds? And it is a request to some of the students who are from SPIT who have really completed the certification to not answer this so that others can really think a little bit. All the other participants, if you're really looking at this, if you could just tell me whether X would be really called every 50 milliseconds precisely. Okay. So this is, somebody has said no. Somebody is saying it will be more than 50 milliseconds. Okay. So that is, Aniket is saying no. Okay. Okay. Somebody could just elaborate a little bit. If you could speak it out, that would be fine. Yeah, I'm getting a lot of. I'm assuming that I have a hardware delay over here, not a software delay. I don't know whether I can really give you that access to speak. Okay, I don't really know that. You can type it out because I don't see any kind of an access for you to speak. Okay. I'll just see the chat then. That's better. Still, the time taken to call a function, even with hardware delay, no software loops aren't precise, depends on time taken to execute X. Okay, Mr. Prabhat Kumar is saying depends on time taken to execute X. And that's okay. Yeah, it will be more than 50 milliseconds is what Satvik Sawant is saying. Okay, fine. I'm getting some answers here. That's nice to see. Right. So I'll take it up. Now, if you see this function X, this X function will run exactly at 50 milliseconds, provided that X's execution time is fixed. If X's execution time keeps changing, the time at which this delay function is called will also change. So assume that X ran for 2 milliseconds in the first run. Then after 2 milliseconds, this delay function would be called. No, and it's a hardware delay. Let's assume it's a hardware delay, so it's precise. So exactly in 50 milliseconds, this function would be called. But now assume that the X function ran for 10 milliseconds. So now the X would next be called in 60 milliseconds. So the time at which this X is called will not be precise if the execution time of X changes for some reason. And it is perfectly fine for a task's execution time to change, unless you know its worst case execution time. But even then, if the worst case execution time is known, even then, without some kind of a mechanism in place, X would not run at the fixed time of every 50 milliseconds. I hope this is very clear to everyone. So with that, at the end, you have to have some kind of a mechanism to ensure this. So this kind of an architecture is certainly not going to help you. Of course, you could do some things like we can have some kind of a sandwich delay in place that will allow you to solve this kind of a problem. But by the, sorry?
Sir, if it was a hardware delay,
Yeah.
Wouldn't we call it before we call X?
No problem. You call it earlier. You call X after that. That is what you're saying, right?
Yes. So then we can, as long as X is less than 50 milliseconds, we can ensure that every 50 milliseconds X will run.
No, 1 minute, 1 minute. Let's call delay 50 milliseconds first. So 50 milliseconds have elapsed. Now the X function is called. Say X runs for 2 milliseconds.
But
X
you
runs
said
for 2 milliseconds.
assume hardware delay.
No. X is an independent task.
Yes, sir.
It has nothing to do with the delay. It has nothing to do with the delay. Delay is just that we have I have put the delay to ensure that X comes every 50 milliseconds. But now I'm saying, now some thought has come to my mind and I start thinking and I come to know that what if the time of execution of X changes every time? No matter X is called before the delay or after the delay. If the time of execution of X changes every time, the time at which delay would be called also will change, right? But the delay's time is fixed. You're getting this or no?
Yes, sir.
So in that scenario, X would not be called at the right time. X's time at the time at which X is going to fire is going to change always. It's not going to be 50 milliseconds precise. It will now not be determined by the delay loop. It would be determined by the execution time of X. Okay. Understood?
Yes, sir. But what I was saying was, if it is a hardware delay, it will run on interrupt sequence.
We are not using interrupts. We are not, the way we are going to use this is, this delay is, it's going to be a flag, polled flag that I'm going to use. I'm not going to use an interrupt. And even if you had to use an interrupt, what would happen if that X was running and it did not complete before the interrupt was raised? You tell me.
Yes,
Would
sir.
your function, would your task really complete on time?
No, sir.
Then is it a good thing to have such kind of a system?
No, sir.
The task is getting interrupted, right? We are talking, see, now you come out of your event triggered concepts. I want my tasks to be executing at the right time and completing at the right time. That is the key over here. Okay. So if it's going to be interrupted, I take your point. I'm using interrupt. Chalo, I'm saying that I'm using an interrupt over here. So if I use an interrupt, if the execution time of the task X becomes 51 milliseconds, what happens? Will your task complete before the interrupt comes? The interrupt would be serviced, right?
Yes, sir.
So once the interrupt is serviced, it will go back to the remaining portion of the X and it would complete that. But by that time, the timer has already started. Remember that. You're getting it?
Yes, sir.
So it's not going to be precise, no matter you use a hardware delay or a software delay. I'm not talking about because it's as it is imprecise. Okay. So what do? We use the timer to interrupt to create some kind of an architecture. It's some kind of an architecture that I'm going to use using the timer 2. Now this timer 2, especially when it comes to 8051, it is a special timer. The original 8051 did not have timer 2, it had just timer 0 and timer 1. So this timer 2 was later on put in by Intel to create these ticks for the system. And these ticks are nothing but periodic overflow of the timer, and they are generated using interrupts. And timer 2 is used because timer 2 is a 16-bit timer. So I can have a good range of tick intervals that I can generate maximum. If it is a 1 microsecond resolution timer with a 12 megahertz crystal, I can generate 65 milliseconds. I can generate a tick interval as big as 65 milliseconds. 60 to be precise, 65.535. Okay. So I'm not going to go through this ritual of actual initializing the timer. It's pretty much known to most of the people who are attending this, because you are from this background. You are actually going to initialize the timer with the load values, and there is a capture register so that there is an automatic reload. You don't use only one point I would really try to make over here is don't use a manual reload, because manual reload will cause some latency. Automatic reloads give you a perfect bang on timing. So use automatic reloads and avoid using manual reloads. So for the automatic reload to happen, you have this RCAP, RCAP too high and RCAP too low. These two registers in which you put the reload value. So whenever the timer overflows, you actually put the timer reload values over there. And then you have your interrupt that's going to be raised when the timer overflows, and you would have some kind of a task executing over there. We'll see this. So now, what is going to be there in that interrupt service routine? The interrupt service routine will actually have the code that you want to generate, that you want to run whenever the interrupt is raised by the timer. And the way you do it in Keil is use the interrupt keyword and then followed by the interrupt number, the vector number that you have. And remember, we had given names to those vector numbers right in the beginning in the project header files. So this line, this red colored line over here that you see, void x interrupt timer to overflow, is actually linking the interrupt to this function. So effectively, this x now becomes the interrupt service routine. Okay, I deliberately use the word function because x is a function. It's a void function. But when you link this to an interrupt using the interrupt keyword, it becomes an ISR. Okay, so that is what we are looking at over here. And there are different kinds of interrupts in an 8051. We have a power on reset. We have an external interrupt, timer 0 interrupt, external interrupt 1, timer 1 overflow interrupt, UART interrupt, timer 2 overflow interrupt. So we are actually using this timer flow overflow interrupt, and its index is 5. So that is the reason you could see that 5 over here. That's your interrupt vector. I generally call it an interrupt vector number because that is how it is. I mean, you should really use that terminology when it comes to these interrupts. Okay. So as I said, use automatic reloads, and you are actually checking whether in this line, this is all the initialization routine of the timer. Now this is a timer 0, just for purposes of understanding. You could very well use a timer 0, but it makes sense to really use a timer that was specifically created for such kind of jobs. So you could also use a timer 0 in that place. But again, remember, as I said, timer 2 was created for this purpose, for creating those sticks. So use a timer 2, and you're good with that. So as I said, this RCAP too high and RCAP too low are actually the reload registers, so that your automatic reload works. So whenever the timer overflows, it would pick up the values from these registers and put it in those timer high and timer low registers, and the timer again starts. So go for automatic reloads. That's the key. Now we are actually going to see our time triggered architecture. And we call it a simple embedded OS. And it's pretty simple. It's actually a scheduler. So what is the architecture? Look at the difference. Look at the earlier code. In while the super loop, I had all my tasks actually running over there. And in this, there are no tasks running at all over here. You can see I'm putting the system to sleep in the super loop. I've just initialized the timer 2 for a 60 millisecond tick interval, and I have a dummy task X that has been initialized. So where are the tasks running? The tasks would really run in the ISR of the timer 2. So I'm putting the task over here. So every time that the interrupt arrives from the timer 2, the task X runs. And this interrupt, as I said, is a hardware interrupt. And since it is a hardware interrupt, there is one more important property associated with this. And that property is directly related to this go to sleep function. Now, what does that mean? Whenever an interrupt is raised by this timer 2, or for that matter, any timer. But as I said, we will stick to timer 2 because this is the purpose of this timer. So whenever that interrupt is raised and the ISR executes, this is the ISR over here. This is the interrupt service routine. It's just running this X task. Whenever this task runs and the task finishes, where does the control go? Where does it go? After this X is executed. Okay, I'm getting some answers. Let me see the chat box. Back to the loop, the super loop, back to the loop, back to the loop, to the sleep. Okay. So people are saying it goes to the super loop, from where the PC came, where the interrupt was called. PC means you're talking about the program counter. That's what you mean? Kush Jain? Yeah, okay. So pretty much true. What we are really doing is the moment this task X completes, we are back into the super loop. That means we are going to this sleep function. Now, what is there in the sleep function? That's the power control register of your 8051, where you actually configure it to put the CPU in the idle mode. Okay. So when the CPU is in the idle mode, you are conserving power. The power consumption is extremely low. So now, when I finish off this task execution, I am back over here and my CPU is sleeping. So I have achieved one thing. I have saved power because now it is not working full power. The while one is not running continuously, just consuming power, running those functions or those tasks which were not really required to be running. So now it's just sleeping over there. But apart from that, it is doing one more important thing. When I put the CPU to sleep, any kind of a CPU to sleep, the CPU is in a known state. And when it is in a known state, you are actually aware of the fact that whenever an interrupt comes, it will awake itself in a specific number of cycles, CPU cycles. And that is known and documented in data sheets. So if you know that it's going to wake up in a specific number of CPU cycles, you know what is the time it's going to take to respond. And that is very critical in time triggered systems. The responsiveness of the system should be known because the time it takes to respond, that is your jitter. Of course, we may not be able to go into the details of all this because that's a subject matter of entire one session. But jitter is what, jitter is nothing but the time that is taken by a task to actually start running. So let's assume that I have a task that runs every 1 millisecond. Now, if there is jitter that comes into play, the task may not start at 1 millisecond. It may just start at 1.2 milliseconds or 1.3 milliseconds or sometimes it may start at 1 millisecond. So the start times of the task keep varying, which is not a good thing. Because if jitter is suffered by one task, it could get cascaded across the different tasks that you have in that particular tick interval, which is not a really good thing. So when you're putting a system into sleep, you are actually knowing how much amount of time the CPU is going to take to actually wake up and start executing the task. So that is the other advantage that you get out of it by putting the system to sleep. So it's anyways a good way of doing it by putting the system to sleep and knowing the exact wake up times of the CPU. So this is the essence of the most elementary time triggered embedded system, and you have actually done scheduling. We'll see the practical example of this now. So you have actually done scheduling. Now there are a lot of other cons that are associated with this particular scheduler that I'm talking about, and there you can then think of some better scheduling mechanisms. That is the time triggered cooperative scheduling that Dr. Pont was talking about earlier. So then you can really see how you can cooperatively schedule tasks, and you can really control their start times, and you can really have different tasks being triggered at different tick intervals. But this scheduler that I've shown you, it's a very simple scheduler, good enough for say around 2-3 tasks. And if at all you have some more tasks and you want to actually have a control over the start times of those tasks, then you have to really think of the other scheduling mechanisms that we have. That is the TTC scheduler. Then we have something called as a TTH, a hybrid scheduler, which is a combination of cooperative and a preemptive scheduler. So there are a range of different kinds of schedulers that we can use with the TT architectures. But this is the first starting point. The other schedulers are based on this idea of the timer interrupt. So now let's have a look at, an actual running system. I'll just open up that now. Okay. So we are using the timer 2 over here, as I said, because that's the one that you have to really use, because the real purpose of that timer was having a tick generated at the correct time. So I'll just share my screen and let's have a look at this now. One with that. Okay. Stop this. I don't want this. Yeah. Okay, so let me open up that code now. I hope you are seeing the code. Is it visible? All of you?
Yes, sir.
Okay. Yeah, so this is our code that we are going to see. This is our last code for this is time triggered system that I'm going to show you so that you get to know the essence of a time triggered system. Fine. So let's begin off with a main.c. This is our main function. Here we are calling the init. As usual, we have the initialization routine for the task X. And here we are initializing our timer 2. So the initialization routine for the timer 2 is set up over here. And you can see that the sleep function is called in the while loop. So no matter what, your system is always going to be over here. Now let's see what is there in this simple EOS.c. So as all of you have seen this in the earlier slide. I have my task over here. Now, what is the task? I have actually done pulse width modulation over here. So what we are doing is we are actually having a tick interval that we have set up over here, right in the beginning in the main.c. You can see that it's a 10 millisecond tick interval. That means every 10 millisecond, the interrupt would be generated. And every 10 milliseconds, this ISR would be called. Now, what is there in this ISR? The first thing that you do is you have to clear the flag that is set when the timer overflows. And then we have a variable that keeps a count. So every time that the interrupt is called, this count increments. So when the count is greater than or equal to 100, that means you have come over here 100 times, right? So you have come over here 100 times. And if the count is greater than or equal to 500, that means you have come to this particular interrupt service routine 500 times. And mind you, every time that you're coming over here, you're coming every 10 milliseconds. So effectively, what this translates to 100 into 10 will give you 100 into 500, what was that? 10 milliseconds into 500 will give you a 5-second time. And this is your 1 second time. So effectively, you are creating a pulse width of 4 plus 1. So if I run this program, and I see this in my logic analyzer, I just run this. Okay, it's already there. I've already set it up and I'm running this. And there it goes. So I have effectively done pulse width modulation. Now, the real essence of this is timing. Let us see what are the timings that we are getting for this particular program. So to do that, first and foremost, let me just place a cursor over here. And let me put a cursor over here. This is my 1 cycle. So if you see this, if you see this, it's around 5.1 seconds is what it is showing you for the entire period. But if I zoom into this, and I really put it up properly, can you see the delta? It's exactly 1 second. So that proves that it's bang on when it comes to timing. Okay. Oh my God, what happened? Just a minute. I think something went wrong with the keel. Just a minute. Something went wrong with the keel. I'll just open it up again. It just closed itself down. Yeah. Just a minute. Yeah. I think now it should be fine. Yeah. Okay. So I was just zooming onto it and you could see that the timings were bang on. And to prove that otherwise also, if I have to put one, say I put a breakpoint here and I run this and I clear this, look at the bottom side of the screen. Keep an eye on this T1 over here. My mouse pointer is over there. And I'm just running this. Look at this. It's 10 seconds, 10 milliseconds. If I run this again, see, look at the accuracy of the timing. So this proves that this kind of an architecture gives you a near perfect timing behavior. And when the system is running, also with the different kinds of the functions or the tasks that I was calling over there, this has really shown me that it gives me the timings that I'm really desiring for. So this is how, this is a basic fundamental architecture that you can see. And if I put a breakpoint here, it will clearly show you that it comes here, it sleeps, and it again goes back when it's time up. It's here, it's there. See, it's coming to the ISR. It's coming to the the sleep function. So it's sleeping. And finally, one more thing before I really close this up. Let me just show it to you in the performance analyzer. Yeah. So this is the function over here. This is the sleep function. If I run this, I'll clear up all the breakpoints now. I'll kill all the breakpoints. And if I run this, can you see something? What can you notice over here? Look at the sleep. The system is sleeping for 99.2% times. And this proves the point that it's actually saving power. So it's actually sleeping for 99.2% of the times. So it's not unnecessarily going through the while loop, doing nothing and conserving power. So you can do your performance analysis of your code and really see how it is translating into a number of different on the number of different performance parameters that we have. Okay. So this is the essence of a time triggered system. And with a little modification to the event triggered architecture that we had been seeing since morning, you can see how effectively we have managed to control the time, how effectively we have managed to save power, and how effectively we have got the accuracy in the timing by just employing a simple scheduling mechanism. This is just, I have just scratched the surface of TT architectures today. There is a lot to it. Many of the participants that are over here, I can see they are from SPIT who have really completed their certification in this domain from us. And they know what I'm really talking about when it comes to TTC scheduling, TTH scheduling. And they have seen how brilliantly these systems work. But for those who have seen this for the first time, at least you have got to know what a TT architecture, what is the starting point of a TT architecture really is. This is just that we have just touched upon one full-fledged working system, which is really, you can say a pulse width modulated output that we have got on our port pin. So any questions anybody has on this? If you want to ask me anything, you can. Okay, somebody is asking, are we saying the jitter in this case is a known value? So the ISR is running every 50 milliseconds plus the jitter interval. The jitter over here, we could say that it's not a jitter. What I said was the time that a CPU takes to awaken. That is, this is to Mr. Gautam who had asked this question. I missed it. The jitter over here is the time that the system takes to really wake up from the sleep. And that is, you can't say it's a jitter because it's a known value. So you have to take that into your system modeling and offset it as you go on modeling the system further with different number of tasks that you have. I hope that answers your question, Mr. Gautam. Yeah. So any questions anybody has? I think that pretty much sums up our understanding of how ET differs from TT and what is the essence of a time triggered system and how to actually effectively create these systems by following some basic simple coding practices, and how to actually have a modular based system, how to actually ensure that all your system related information is in one place and not scattered around. So that these are some of the starting points of a good system design, no matter whether you're working in ET or TT. But this is how you should really start off with your system to make a system reliable. So reliability, safety, time triggeredness, all this is key in a time triggered architecture. Any questions anybody has regarding this? These codes are not shareable at this point of time. It's not in the open domain. But these are the ones that we generally use during our training sessions. And we cannot really, I'm really sorry that we cannot really give it to you, because this is all copyrighted material and it's patented technology. Without expressively getting a written permission from safety systems, we cannot share this. Even for academic research, you need express permission from safety systems, even if it's going to be used in PhD theses or anything of that kind. Because as you saw in the earlier session from Dr. Michael Pont, it was in the, they have non-disclosure agreements with the clients with which they work because of the competitiveness. One of the examples is the electric vehicles. They cannot share some of the technology and the techniques that they have used in their trucks, because other truck manufacturers or other companies can really have a competitive edge if they get hold of that. So it's under the non-disclosure agreements that many of these things work. Yeah, I think that answers your question. Is the current code ISR called in 10 milliseconds and for the rest of the time system is in sleep mode? Yes, the ISR is called every 10 milliseconds, and the rest of the time, of course, the time that it takes to go through that ISR, that time it is awake. The moment the ISR finishes, it goes back and sleeps, and it will sleep for the next 10 milliseconds. Satwik. Okay, Janil is asking, instead of T word, how about using unsigned int? Yes, you can use unsigned uint underscore 8 T. This is because the new C99 standard encourages the use of this. This is the reason, you know, why this particular keyword was introduced. Instead of unsigned int, we use uint underscore 8. 8 says that it's an 8-bit variable. If it's a 16-bit, put 16 over here. If it's 32-bit, put 32 over here. So that solves the problem of actually knowing what kind of the variable that was, an 8-bit or a 16-bit or a 32-bit. So, but for, 8051 related projects, you can certainly use this T-word technique. But for 32-bit and all, you can certainly switch over to uint underscore 8T. That's right. I hope I have answered the question of Satwik and Janil.
Govind sir, from your side, anything is remaining?
No, from my side, everything is done. We're done with it.
Okay, then I think we will not take any more questions now.
Yeah.
And we will go ahead with our plan, because already it's the 5:15.
Yes.
Okay,
Yes. So I'll just finish off with the final closing slides, and then you can open open the quiz, sir.
Yeah.
Yeah, just a minute. Give me. Yeah. So I'll just share that screen. I just need another 5 minutes and we are done. So I think you can see my slides.
Yeah, we can see.
Yeah. So at the end of it, I would like to announce to all the participants that Microdevice Technologies is a strategic training partner of Safety Systems Limited. And we represent them in India, and we offer their international certifications in this domain to all the participants. And one more thing I would like to add over here, with Rathod sir's permission, that we are in the process of really working this up with SPIT and trying to open up these certifications to all the participants, and you can join these courses through SPIT. Of course, that's in the process, and SPIT could become the main center for this if all things materialize between us, and it could be a main center for delivering these courses, and they would be delivered online using Keel simulator and on an ARM Cortex derivative. So whatever that you saw, it was just a snapshot of what the course is all about. And you would certainly be learning lot of things with the different levels of certification. So I'll just quickly go through the certification levels. So with these certifications, you get us internationally, you get an international certification from Safety Systems. And the entire course curriculum, the structure has been created by Safety Systems. And we would be using their technology in training you up for understanding how TT architectures are made and how to make your code safe and reliable. So that is the basic idea behind these certifications. And as I said, we are the sole authorized training partner of Safety Systems. We offer level 0 and level 1 international certifications from Safety Systems under the licensed safety certified track. And as I said, we are in the process of opening up the tracks for candidates across Indian academic sector through SPIT in Indian currency. So it's not going to be in pounds. The cost of the courses in pounds is exorbitant, which is not affordable by most of the participants in India. So it's going to be in Indian currency and at affordable price points. And they would be live and through Zoom and fully online using ARM Cortex MX architectures using Keel's simulators. So you can download the Keel simulator and you can use it, and we will go through that entire process of doing that. And you can also log into our website at microdevice.in if you want to take up these courses quickly. We have an online payment module also over there, so you can join these tracks in individual capacities. So there are 2 international tracks that we are offering. Level 0, this is for candidates who don't have any kind of background in even microcontrollers. We start from there and then we advance up to the fundamental building blocks of TT architectures. So this is for all participants who have no idea of what a microcontroller is. So we start from there, and we would be doing this on ARM Cortex derivative on Keel. And then once you finish your level 0, you can go to level 1, which is the next level where you would be learning to create your own schedulers, like the time-triggered cooperative scheduler that Dr. Michael Pond was talking about, the time-triggered hybrid scheduler that he was talking about, and move towards functional safety. So this is the advanced course. And one more thing that I would like to add finally is now we have also signed up with LPI, which is a Canada-based non-profit organization which offers vendor-neutral certifications in Linux. So you could take these certifications right from the comfort of your home. You can sign up for these, these exams, and it would be conducted via Prometric Pearson VUE proctored exam online through your home. And we are also looking at SPIT to be a channel partner with us on this as well. So this is the latest development that we have. So you can, and we are going to give you a 30% discounted voucher for taking up any of these exams on Linux. There is a Linux Essentials, Linux 1, LPIC 1, LPIC 2. Like it goes up to the most advanced level of Linux certifications that you can acquire sitting here in India. It's next to Red Hat certification track. You can just check out LPI website and you can get more information and you'll come to know what I'm really talking about. So these vouchers are up for grabs for all the participants. We have, I think, around, so how many? 69? Yeah. So you're getting a 30% discounted coupon, which is valid for 1 year. So during the 1 year's time, you can really use this coupon and you can complete your certification exam. So it's a great discount that you're getting. And you have 1 year's time to prepare for these exams as well. Yeah, that's it. Thank you very much, all of you, for patiently having listened through the entire day and having attended both the sessions. We thank you very much for your participation. Thank you, sir. Thank you, Rathod, sir, and thank you, SPIT organizing committee of this fantastic conference, which they have done online, which is a Herculean task in its own. Doing things physically and doing things online are really very difficult. So thank you, Rathod, sir. Thank you, Reena, madam. Thank you, Bhagat, sir, for all the help that you have been offering me throughout the day. Over to you, sir.
You're welcome.
Thank you, sir. Thank you very much. So now we will complete for which many participants probably are waiting. So, but before that, let me summarize and tell what sir has told.
Yeah.
So we already had one of the assessment in the morning. Now we are going to have in the similar way. I will put up the link in the chat box, and you are going to answer within the 10 minutes. 10 minutes is the hard deadline, time triggered. Okay. So within those 10 minutes, you have to answer. I hope everybody got my Dr. Michael Pond's handouts, which he has provided to me. I had already put into the chat box, but there are people who were not able to get it. So if you could not, then put in the chat box. We are still not able to get it. I will put it again. Okay. One request is about the feedback form, which Bhagat sir has already shared in the chat box. Please fill this feedback form. Okay, you keep it open, that link open. When exam start, don't fill the feedback form first. First, you complete the examination. Okay. And the next thing is, last time I would be announcing this, which Govind sir has already announced. Out of these attendees, we will be having top 20, and then sir is going to finalize about the 10 winners who will be getting the boards, and the 10 winners who will be getting the provision of attending their training programs, full-fledged training programs. Okay, you will get this email from us, from our side, from my side. You will get this email within next 4 to 5 days, maximum 5 days. We don't need 5 days, but to be safe, I'm giving you the 5 days. If you don't receive an email, don't please reply that we are not received. If you receive, it means you got it. If you are not received, that means forget, you are not made it. Okay, but you will definitely receive one thing, that is the exam voucher. This exam voucher is not given in general. That is through our tie-up. Govind sir is able to convince to LPI that all attendees in this training session should get a voucher, and we are able to get that. In fact, we got 170 vouchers, and we could see only 70 are there still. So, okay, anyway, so every one of you is going to get an email about those vouchers. So if you are interested in the Linux examinations, any course related to Linux, you can learn that within a year, and you can appear for certification. In that certification, you are going to get a 30% discount. That is what is that voucher is about. Okay, so you can keep that voucher with you for entire 1 year. So that's the next thing. And those who are going to score, I think Govind sir said 70%.
Yes, sir. 70% marks.
Yeah, 70% marks in collectively together in both the assessment.
So that means 15 marks or more.
Okay.
Collectively.
Okay. So they will also get one extra certificate from MicroDevice because you have excelled in these two assessment tools. That means today you have performed very well. So one additional certificate. So there are many things. One certificate from sir, one certificate from our side, SPIT, that you have attended the course, from sir side because you have excelled today, and those 20 participants who are going to get a separate email. Okay. So good, very nice. So I'll end my speech with this thing, and I'm going to put now in the chat box Google link. Okay.
सर
So,
नो वोट ऑफ थैंक्स है उसके बाद
हाँ वोट ऑफ थैंक्स है। तो वो मैंने उनको मेरा बता दिया ताकि समराइज किया मेरे साइड से क्या क्या है। ठीक है। So let me put this link. Okay, link is there. Oh, sorry. Chat box, everyone. Sorry. Now link is there. Okay. So your exam started 5:28.
5:28. 5:38 we close.
Yes. Go ahead. Best of luck. Bhagat sir, you appear.
Sir, submitted.
Responses started coming. Still, you have time, enough time. भगत सर आप शेयर कीजिए स्क्रीन, चलेगा तब तक ना?
करूँ सर?
हाँ स्क्रीन शेयर करो ना, स्क्रीन शेयर करो. Now still 5 minutes are there.
Yes, 5 minutes.
Govind sir, we have an excellent candidate. You will have a tough time.
Yeah, I have seen that in the morning. Vote of thanks.
सर दिख रहा है ना?
Yes.
और मेरा आवाज आ रहा है ना? Am I audible?
एकदम मस्त.
Okay.
बस अभी 4 मिनट होने दो. Yeah, last 2 minutes, huh? Make sure that you respond within time, last 2 minutes. So it's actually last minute. Great. Suddenly 50 responses received. So hurry up, last minute is going on. It should not happen that I close and then you submit.
I think it's going to be a photo finish.
Yeah, now time is over. Time is over, I'm going to close. So I can see that 5, 6 are remaining. Quick enough. Submit, submit. I'll close, closing. Time triggered. Share code to close. Yes, done. Thank you. Yeah, done. I have closed the quiz.
Great.
So Bhagat sir, over to you.
Thank you very much, sir. Am I audible?
Yeah,
Yes, yes.
Okay. So I'm here to present the vote of thanks for the whole day. So ladies and gentlemen, I feel greatly honored to present the vote of thanks at the end of this tutorial session. I wish to thank the Bharatiya Vidya Bhavan's management. I'm particularly grateful to Principal B.N. Chaudhary sir, our mentor and leader, our General Chair, Dr. Y.S. Rao, and Dr. Dhananjay Kalbande, our tutorial chair. It is my privilege, pleasure, and honor to offer my deep gratitude to the eminent speakers, Dr. Michael J. Pond, founder and CEO Safety Systems Limited UK, and our own Mr. Govind Gaundalkar, engineer at Micro Devices Technology, certified by Safety Systems UK. I thank them for taking time out from their busy schedule to attend this tutorial session. We are enlightened by the encouraging words from them. Thank you. I also appreciate Professor Surendra Rathod and Professor Reena Kumbare for giving day and night support and being resolute and responsive to the challenges we faced in last few days and making the whole session a great success. I thank the team of committee members who helped to conduct the session smoothly. Finally, I thank our audience, including outside participants who had made this tutorial session a great success. Thank you all. Thank you. Thank you, sir.
Thank you
And
very
Govind
much.
sir, this is as usual for you.
Thank you very much, sir.
Soft copy. Virtual moment.
Thank you. It was great doing this tutorial, and I thank all at SPIT, the committee of the organizing committee of this conference, the principal, then especially a special thanks to Dr. Surendra Rathod, then Professor Bhagat and Reena Madam for being over here for the whole day and managing things in a very, very efficient way, as they generally do. I mean, it's in their DNA to make things successful and manage them in the most efficient way. Thank you very much. And we really look forward to be working with SPIT in the future. Thank you.
Thank you, sir.
so
Thank
much.
you. There are few participants who had pinched in that they could not see the Dr. Michael Pond's handouts, which I had put up in the chat box. Is there anyone like that? Madam, now we can stop the recording and live streaming, I suppose.
Okay, sir.
Yeah. So is there anyone who has not received? I can put it into the chat box again.